Hi. Yes. Oh, okay. Works. The mic is also. Yeah. I just kind of. Hi, good morning, everyone. I think we'll just go ahead and start. Sorry for the slight delay. And I'm really happy to see many early birds here to this DeepLo workshop and NAACL. We're really excited. As you can see, this workshop is organized by a diverse group of people from both industry and academia. And the reason we organize this workshop, as you may already well aware of this, is that the data set is very scarce. It's very labor intensive and expensive to construct data set. And in the meanwhile, there are so many different languages in domains and modalities are there that we need data set from, right? So with this, I think it's a natural question to ask, how can we build models that work for low resource setting that we need less data and that can generalize to all those different languages, domains, and modality? So I think that's this question and motivation that brings us to be all here. So I'm really excited to see we have a cohort. And then the purpose of this workshop is, of course, discuss this challenging problem and to tackle important problem on low resource NLP across industry and academia. And we're trying to understand the limits and the current challenges of for low resource NLP. And we're also trying to foster interdisciplinary collaboration and discussion on these very important topics. With this goal in mind, we have a lineup speakers, Sebastian Ruder from Google, David Ifeoluwa, Adelani from Salem University, Yulia Tsvetkov from University of Washington, and Graham Neubig from Carnegie Mellon University. So we will hear their perspectives on the problems and the solutions from both the perspective from industry and academia. And I also want to give people a little bit of an overview of how many submissions we've accepted. We accepted 36 submissions from them. We accepted 23. So it's actually quite competitive selection process. And among this, we selected 2 best paper award by all the committee members voting on all these papers. And I also draw a word cloud for all the papers. One thing I want to clarify is you can see, of course, BERT model and then low resource or something, resource language, domain adaptation, or short cross, like a few short or cross language, all that are the theme or topic of the works that presented here. But I also want to point out that although these words are sort of more higher frequency, they're not that higher frequency, more higher frequency than other words. So in other words, the topics that are presented in this workshop will be very diverse. That's something I'm really excited about, to see people bring different angle into this problem space. And then a little bit of the schedule, which you can find on our website. For the morning, I'm doing this opening remarks, and then it will be followed by an invited talk, and then we'll do a spotlight talk to the 2 best paper award. And then we'll have a coffee break, followed by another invited talk, and then we'll have a virtual poster section. I want to clarify that the poster session, the reason it's virtual is all the presenters are not here. So I really encourage you, if I know there could be a little bit of a challenge while you navigating the space here, and then find somewhere to join the virtual poster session, but I really encourage you to do so. And then in the afternoon, we have another invited talk and a second poster section that would be a hybrid. So most of the people that the presenters for these papers in the second section will be in person. So you will see their poster in the 7th floor. But in the meanwhile, there will be another parallel session for people who couldn't make it or could not make the morning session for the virtual people. They will have a virtual poster session as well. And then it will follow by a coffee break and then another invited talk. And then we'll close. So this is a very good, interesting schedule. So I hope you will enjoy this, the 4-day schedule. And here I also want to express our hearty thanks for all the committee members to help us review and recommend the best papers. And we also are grateful for the sponsorship from Google and eBay. We raised $3,500, and all of these are contributed to the DEI effort to the main conference. So we're really proud of that. And these are the organizers. Me, Shang, Swapa, and Sharon are here in person. Unfortunately, the other organizers cannot make it in person, but we put quite some effort in organizing this workshop. So we really hope that you will enjoy it. And then without further ado, I think don't forget to tweet for this workshop if you see see the interesting talk, see good work. If you have any questions, most of the information are available on our website, and you can also find us via Twitter with the handle DeepLo NLP. So without further ado, I want to hand over this stage to Swapa to run the show. Thanks, everyone.
Morning, everyone, and thank you for being here after 3 days of NAACL and being here early. So it's my distinct pleasure to introduce our first invited speaker, Sebastian Ruder. A lot of you might know Sebastian from his periodic newsletters and blog posts about the current and exciting trends in NLP. More formally, Sebastian is a research scientist at Google Research, working on NLP for underrepresented languages. He was previously a research scientist at DeepMind London. He completed his PhD in NLP at the Insight Research Center for Data Analytics, while working as a research scientist at a Dublin-based text analytics startup, Alien. Previously, he studied computational linguistics at the University of Heidelberg, Germany, and at Trinity College in Dublin. He's interested in cross-lingual learning and transfer learning for NLP and making ML and NLP more accessible. So Sebastian is currently based in Berlin, and we thank him for joining us at this late hour. And today he'll be talking about the efficient methods for low-resource NLP. So I'm hoping we can just transfer over the stage to Sebastian now.
Cool. Hey everyone, can you hear me?
Yes, we can hear you.
Awesome, cool. Thanks a lot for the introduction, Svava. Let me try to share.
Hey, Sebastian, can you hear us? You're muted.
Yeah.
We can hear you now.
Yeah, right. Okay, I've had this in the past. When I share the screen, I'm getting auto-muted for some reason. Or let me. Okay, is this better? Yeah. Okay.
Yeah, we can hear you.
Sorry about that. Cool. Yeah, at Google we have Google Meet, so I'm not that not using Zoom that much. All right, yeah. So thanks so much for inviting me here. I'm really excited to speak to you, if only virtually. And today I want to talk to you about efficient methods for different low-resource settings, with a focus on multilingual applications. And just to set the scene a bit for the types of settings where these approaches may be useful, I want to preface the talk here with talking about kind of one pervasive issue in NLP, which is the issue of language diversity. As probably most of you are aware, there are around 7,000 languages spoken in the world. And to provide a bit more detail, about 400 of those languages are spoken by more than 1 million speakers, with about a little bit more than 1,000 languages being spoken by more than 100,000 speakers. So we are by far not talking about small speaker populations here. However, most of those languages, if we want to use them with our current NLP technology, we are faced with the challenge of limited amounts of both labeled and unlabeled data. And this is a big challenge and a big impediment to enabling progress of recent technology in NLP for these languages. And to kind of illustrate that a bit more, here's a figure from a paper by Yoshi et al., where they categorize different languages based on the amount of labeled and unlabeled data that is available for those languages. And as you can see here, they categorize them into 6 different groups based on the availability of different data sources. And most of those languages, however, fall into these groups 0 and 1, where the group 0 basically has virtually no textual data, be that unlabeled or labeled available. And furthermore, around 5% of the world's languages also have very limited resources available. So very few labeled data and some amounts of unlabeled data as well. So when I'm going to be talking about low resource settings or low resource scenarios throughout this talk, I'm going to be referring to these limited amounts of data that are available for most of these languages around the world. But beyond that, however, many of these underrepresented language settings also face constraints that go beyond data. So if we want to apply our technology to languages in different countries, many countries, mobile data, for instance, like you can see on the right, is much more expensive compared to countries in Europe. Also, other computational resources like compute or RAM might be much more expensive or often unavailable in larger quantities. So based on these considerations in general, challenges, these essentially motivate the topic for my talk, that we should develop not only methods that are more sample efficient, so methods that can not only do more with less data, but that are also efficient in terms of the space that they require, and in terms of how fast they can run during training or inference time, to limit the amount of compute that we require for them. Just for some additional context, of course, the area of making NLP methods more efficient has seen a wide range of different methods and wide range of different literature proposed. And there are many different methods for different areas. For instance, for sample efficiency, there are a lot of different approaches in terms of developing better pre-training objectives to make models more sample efficient, as well as better architectures, so modifications of recent transformer architectures, for instance, to make models learn with less data as well. On the space efficiency side, there are also a wide range of different approaches like pruning, distillation type approaches, or quantization methods that you can use to make a large model quite a bit smaller. And so for this talk, I'm mainly going to be focusing on methods that are particularly useful for low resource multilingual settings. So whereas most of these general methods can be applied and indeed have been adapted in multilingual settings, I'm mainly going to be talking about methods that have been specifically developed with the challenges or characteristics of multilingual settings in mind, to work well and to be more efficient in those settings. So with that in mind, there are 3 dimensions of efficiency that I want to talk about throughout the talk. The first one being sample efficiency, so trying to learn with limited amounts of data and reaching kind of a given performance with fewer data than comparison methods. I'm also going to be talking about space efficient methods, so methods that are just smaller or require fewer parameters than their counterparts, as well as methods to run faster, either during inference or during training compared to comparison methods. So with that, on the sample efficiency side, there are 2 types of categories that I'm going to be discussing. The first one relates to using language-specific inductive biases, and one particularly promising source of bias here is with regard to the level of word representation. So how can we improve the representations on the word level, or the way words are segmented into different languages, in order to improve learning in our methods, as well as the use of alternative data sources. And in this talk, I'm going to give one example, which is using bilingual lexicons as one additional data source to learn with less unlabeled data, but exploiting this additional alternative source of data. So with that, here most current methods these days, whether they are monolingual or multilingual, rely on subword segmentation. So in order to pre-process the input, they run it through a learned subword segmentation algorithm like BPE that was trained on typically the same corpus as the model is pre-trained on, and has learned to split words based on the frequency of different subwords into different constituents. This works quite well in English or in similarly morphologically poor languages. But as you apply the subword segmentation to settings where you have data in many different languages, which also has different amounts in different languages, with languages based in Europe, in European languages typically being overrepresented, you run into certain challenges. And one of the most common challenges here is that words in languages with a lot of data tend to be under-segmented. So if you take a word in English, like excitement here, and run that through the segmentation algorithm from a popular multilingual model like XMR, you get a single subword that is assigned to this single English word. However, if you run words in languages with fewer data through the same segmentation algorithm, you get them split into much more subwords, and many of them often not really aligning with the actual linguistically useful morphemes that we know of. And you can see some examples in still quite high resource languages, and this problem is even much more severe in languages with much fewer data, where in some cases you have individual characters being assigned individual tokens, because the overall tokens appear so unfrequently in the data. to provide a bit more context of these different segmentation algorithms, what we are using in our standard models is known as deterministic segmentation. So for a given input, given our trained segmentation model, we are getting back deterministically a single segmentation sequence. However, there are also probabilistic segmentation methods that, given a single input, can give us a number of multiple candidate segmentations. And we can choose the most likely one or use different segmentations. The most kind of useful way to use these probabilistic segmentations is to use them during training, kind of in a similar way that people have been using dropout to make a model more robust by essentially exposing it to multiple possible segmentations during training time, so that at test time it is more robust to different errors or to alternative forms of segmentation. And this is a method that has been successfully applied in some methods in machine translation. So we can basically try to also apply the same method, so this subword regularization, where we use these multiple segmentations, also when we fine-tune our multilingual models on English data to make them more robust for then performing zero-shot transfer to another language. And this is kind of where the method that we propose here comes in. But one kind of key consideration here that is different from the machine translation scenario is that when we apply probabilistic segmentation to our models, we introduce a mismatch compared to the pre-training setting. Because during pre-training, the models have only seen the deterministic segmentation. So if we now use these probabilistic segmentation during fine-tuning, there might be a mismatch and consequently poor performance on the model side. So in order to basically leverage and get the best of both worlds here, we can combine both of these segmentations during training. So given an input here, we can both obtain our deterministic segmentation and consequently the cross entropy over the deterministic output with regard to a specific task. And we can do the same thing, but now over a probabilistic output as well, and combine that into joint cross entropy loss. However, by simply just combining these objectives, we're not really making sure that our model is actually consistent with regard to its predictions across different potential segmentations. So we can additionally introduce an additional auxiliary term here that you can kind of see as being similar to approaches that have been used in semi-supervised learning to ensure consistency between different views of the same input example under different forms of data perturbation, for instance. And in this case, we essentially can introduce consistency using a KL divergence term between the probability distributions from our deterministic output compared to the probabilistic output. And it's essentially enforce that our model produces consistent predictions no matter the segmentation that it receives from the segmentation algorithm. And we can combine both of those objectives, the cross entropy term and the prediction consistency loss, then into our final kind of joint objective. Now, with regard to results, we basically apply this in the standard zero-shot transfer setting, where we have a model, multilingual model like multilingual BERT XLR, that is being fine-tuned on a task, on one of these tasks here on English data, and then being transferred to another task at test time. And you can see here the improvement versus kind of the standard model with our method on top, as well as with standard with this subword regularization that I mentioned before. And we can see that in most cases, just applying subword regularization just on the English data already improves performance quite substantially. And beyond that, applying multi-view subword regularization, so considering both views as well as the prediction consistency term, improves performance even further. And I think the nice aspect of this method in particular is that because we only need to apply this regularization during training, we incur no limitations and no performance, no runtime decreases at inference time. So the model can just be applied as is at test time, and we only need to apply this regularization during training time and only on English data. And to give you a bit more insight into where this method works particularly well, we can plot here the performance of languages that have a Latin script versus languages that have a non-Latin script, where the non-Latin script languages have a darker color on the plots here, and we again see the gains over the baseline. And as you might expect, because for most languages that are underrepresented, many of them have a non-Latin script. And for most of these, we might expect that the segmentation algorithm that we have learned may not be as good as for languages with Latin scripts. And indeed, we can see that this method of making the model more robust to segmentation errors actually helps most for these non-Latin script languages as well. So with that, I just want to, so basically I've highlighted kind of one way to introduce inductive bias into the model by trying to overcome some of the limitations of the underlying segmentation algorithm that is used kind of in the standard setting in current multilingual methods. And I just want to kind of end this part here with a couple of other pointers to related work. In particular, recent work has kind of beyond trying to modify the and building on top of the segmentation algorithm as we've done, people have recently also modified the segmentation algorithm directly, either by preferring tokens that are shared across many languages, so kind of introducing this as additional inductive bias, or modifying the segmentation splitting algorithm to preserve the morphological structure of the tokens, so to prefer kind of longer rather than shorter subwords as it splits the model, as it splits words into different constituents. And beyond that, we can also think of alternative pre-training objectives that take into account the different morphological phenomena. So we are still, in most settings for multilingual models, doing this either whole word masking or masking different subwords. But for many morphologically rich languages, we could also imagine incorporating some information about the morphology into the way we mask subwords as well, for instance, by masking inflections or different relevant morphemes. And beyond that, in many morphologically rich languages, for instance, one spoken in Africa, tone is quite important as well. In some languages like Yoruba, where tone is marked, we could also try to explicitly incorporate how we model or distinguish different lexemes with different tones as well. So in Yoruba, for instance, you have 5 words that are spelled the same, but with different tone markers, which have completely different meanings. So these are things that I think we can do a better job of actually modeling explicitly, and which might particularly help for some of these morphologically rich, underrepresented settings. Now, going to the alternative data side, there are a number of resources that are currently or have been used to train models from using Wikipedia or Common Crawl as common source data, and these, so Wikipedia and Common Crawl, as you might see here in the graphic, cover about 4% only of the world's languages. If we go beyond that, the Bible covers around 23%, and has also already been used to fine-tune multilingual models, specifically on data in those languages which are not covered by Wikipedia or Common Crawl. However, so far, one resource that covers a much larger variety of languages has mostly gone unexplored, which are bilingual lexicons. So lists of translation pairs between typically English and another language, where you have essentially words in English and their corresponding translation into the target languages. And large bilingual lexicons like Panlex cover already about 5,700 of the world's languages. So given kind of state-of-the-art multilingual models, which learn typically from large amounts of unlabeled data on the web and are typically rarely exposed to word pairs in isolation, how can we use these bilingual lexicons effectively to also improve the learning of these methods? And one method that I want to talk about here, that is work with these collaborators, is by using these bilingual lexicons to generate additional synthetic data. To see how this synthetic data can be used, I'm just going to show you here basically the 2 main ways we can currently use additional data to improve the performance of the model beyond pre-training. A standard method here is to use additional monolingual data in the target language to additionally use this monolingual data to fine-tune our model using masked language modeling on this data, and effectively adapt the model and make it more useful and more specific to data in this target language. And this, typically after that, we then still fine-tune it on data that is specific for the target task. Beyond that, we can also use parallel data for different languages, or task data directly by using a machine translation system to translate data that is typically in a high-resource language like English for a given target task to the target language directly, and fine-tune the model on this translated training data. And that's why this approach is typically called translate-train, as we translate the labels training data for a given task. Now, consequently, we can similarly use building lexicons to augment and generate two types of synthetic data as well. So in the first setting, we can use building lexicons to essentially replace the English monolingual data that we have by simply performing word by word translation. So by translating, by replacing a word in English with its corresponding translation if it is available in the lexicon in the target language, and use this kind of as additional pseudo monolingual data in the target language because it covers target language words, but arguably doesn't really represent the structure or the concept of the target language. Similarly, we can also do the same for the English task label data that we have available. So we can also use our building lexicon to replace the data of our target task, again, word by word here. And there are a couple of additional things, as you might expect. The quality of these pseudo datasets might be questionable. So we can do a couple of things as well to improve potentially the quality of these pseudo monolingual data sources. And in particular, we can try to, if we have additional parallel data available between English and the target language, we can use this additional data to learn word alignments to improve the coverage and the quality of our building lexicon. And we can also do label distillations. So we can use our English task data to train an initial model for the task and to generate additional pseudo labels on our pseudo task data that may be better or might take into account some limitations in our translation process. For instance, for part of speech tagging, where through the lexicon replacement process, the part of speech of a word may change during the process. So let me show you some results now in terms of how using both of these methods compared to baseline can improve performance. And in particular here, similar to what I mentioned like all the way back in the introduction, we can differentiate between two settings. One is kind of this no text setting where we have literally no available text data in the target language at all. And we are the only data sources we can get are from these pseudo monolingual or pseudo translate train data. And in this case, in the setting where we have literally like no data for the target language, we can see across basically different tasks here that pseudo fine-tuning, so basically using the task specific data and replacing words there with our words in our lexicon, generally improves, achieves the best performance even over a combination of the two. If in addition we have some amount of monolingual data, like from the Bible, to also use this monolingual data for adapting our model and fine-tuning it on masked language modeling on the data we have available, we actually see that using pseudo masked language modeling, so combining this gold data in the target language with this additional pseudo augmented data can further improve performance in most cases. So with that, I want to conclude this section, and the main takeaways really are that I think while as a community or in general as a field, I think we've kind of moved away from inductive biases and have kind of moved to making our models as general as possible. I think inductive biases are really very useful and particularly useful in these low resource multilingual settings. And furthermore, I think given that current models consists of a stack of multiple layers, I think the best or one of the best cases or sources where we can incorporate these inductive biases are really on the input level or on the segmentation level in terms of improving that, particularly for morphologically rich languages. And beyond that, I also think a lot of alternative data sources are unexplored and are really actually crucial, necessary to explore, given that what we've been using so far for training our models only covers about 4% of the world's languages. So if we want to really scale our methods to the next 1,000 languages, we really need to look for alternative ways to either use alternative data sources or additional ways to actually generate or elicit new data. So with that, here in the next section, I want to talk about kind of one general method, but one that I think is particularly useful for multilingual approaches, and that regards adapter layers. And adapter layers you might have already heard of, can basically be used here in this multilingual setting to allocate additional capacity for specific languages. So for languages that are typically underrepresented during pre-training and consequently in the parameter and representation space of the model, we can use these additional parameters to make the model more powerful and more suitable for those languages. And these adapter parameters are typically small bottleneck layers that we insert into an existing pre-trained model. So in practice, we can have here a single transformer layer in the encoder. And then to insert the adapter layer, we take this, pull this layer apart, and put the adapter layer typically just before the output layer normalization. And the adapter layer, as you can see here, is basically just connected with the rest of the model with a residual connection and consists of a single feed-forward up and a single feed-forward down projection. And typically, we treat these adapter parameters as being separate from the remaining parameters of the model, because in general, the main benefit of the adapters comes from their ability, if we apply a model to different settings, like different languages or different tasks, or even if we just take different checkpoints doing fine-tuning. Typically, we need to store a single copy of a model for each setting if we fine-tune it. However, with adapters, as we keep the underlying parameters of the model fixed, we only ever need to store a single copy of the underlying model, and just a single copy of the and a copy of each adapter layer for each setting, which are much more smaller and much more parameter efficient. So in the multilingual setting, the main benefit or the main usefulness of the adapters comes from their ability to learn transformations or that make the underlying model more suitable to different languages. And in the multilingual setting, we can achieve this by using a task for which we have a lot of data in different languages. Typically, we use masked language modeling, so just a pre-training task for that, to train our adapter layers for different languages, like here for English or Quechua, for instance. And then, given that we keep the underlying model fixed, these adapter parameters are essentially interchangeable. So we can remove the English adapter parameter and just slot in the adapter parameter of another language and have a model, and like that, turn a model that was suitable for English or model to a model that performs better in this new target language. And I think this kind of aspect, this plug and play, kind of slot in, slot out property of adapters, I think it is one of the biggest promises of these types of additional like language-specific capacity approaches, as they allow us to be much more modular with the design and the way we use our models in practice. So rather than having our single monolithic model that we have to use as is for our target setting, we can now simply swap in these different layers to make our model more suitable or to combine information from different tasks and languages. And to highlight one approach or one way that we can compose and combine these different forms of information, which we termed MEDEX here, which is kind of joint work with Jonas, Ivan, and Irina. As part of this framework, we can learn both language and task adapters. So the language adapters we can train, as I already mentioned before, by just using masked language modeling to train a specific adapter, freezing the remaining parameters of the model on using masked language modeling on the Wikipedia of the relevant language. Then, as we typically want to apply these models to a target task of interest, we can stack an additional adapter that captures now properties of the target task. on the initial source language adapter. And in practice, we typically freeze both the language adapter and the remaining transformer weights, and then only train the task adapter, so that hopefully, while the language adapter captures properties of the language, the task adapter will hopefully mostly focus on capturing properties that are relevant for the target task of interest. And then I think the really nice aspect here is that in order to do zero-shot transfer now, we can just simply slot into and replace the source language adapter of English now just with the target language adapter that we trained previously, and expect that the model will do reasonably well on our target language, provided that the task adapter is reasonably language agnostic. So now to kind of show where and in what settings this approach works well, we've done different evaluations, but I just want to highlight an evaluation on cross-lingual named entity recognition, where you can see here the cross-lingual transfer performance from different source to different target languages. And the source and target languages are roughly sorted from left to right and top to bottom, based from high resource to more low resource and unseen languages, and languages that have been unseen during pre-training. And we can see here, in general, given that there are mostly different shades of green in that diagram, that MADX outperforms, so MADX plugged into XLMR, outperforms XLMR on about 16 out of 18 target languages. And what is particularly promising is that allocating this additional capacity using adapters performs particularly well, as we might expect, when transferring from high resource to low resource languages, which might be, again, underrepresented in the embedding space. However, still quite convincingly, the model still achieves competitive performance even on related high resource languages. So even in the settings where we would assume our multilingual model already performs well on, the adapter still is competitive and kind of a useful replacement. Since we've kind of proposed or had this original paper on that work, adapters have been used in many different monolingual and multilingual settings as well. And so I just want to highlight a couple of additional benefits just beyond their sample efficiency and their parameter efficiency of these adapters. And in particular, one nice thing of adapters compared to standard fine-tuning, whereas with standard fine-tuning, you typically update all the parameters of the model. With adapters, as you only update a small number of parameters, adapter is actually much more robust to different hyperparameters and different hyperparameter selections. So for instance, you can see here from a recent paper, some experiments where they had different runs with different learning rates for a BERT model on different glue tasks with different numbers of training examples. And you can see here that with the blue numbers, which is standard fine-tuning setting, as is quite well known, for certain learning rates, the model's performance deteriorates sharply or collapses, or the model completely fails to learn anything during fine-tuning. But adapters' performance, even across different learning rates, is mostly quite stable. So in practice, using adapters actually requires much smaller or much narrower hypergrid or hyperparameter searches. Beyond that, and beyond kind of the absolute performance improvements, adapters can also lead to increased sample efficiency because they're also less likely to overfit in practice. And finally, compared to other kind of parameter-efficient methods like continuous prompt methods, where you prepend a continuous prompt rather than a discrete prompt and use that kind of as additional parameters for learning in our models. And for these methods, people have also shown that they are quite sensitive to different hyperparameter choices, whereas adapters are more robust as well. And finally, I think one really nice aspect about this kind of methodology is that it's quite flexible to different potential extensions. So people have recently, for instance, incorporated hierarchical structure by using different adapters for different hierarchical domains, and then either stacking or averaging the representations of these different adapters to kind of combine their information. And these adapter layers can also be generated, and through the generation conditioned on different other types of variables, like the input directly, or even different typological characteristics of the different languages. And while I've mostly talked about adapters, I think the general concept of using or allocating additional language-specific capacity is kind of more useful or useful beyond adapters, and particularly useful for underrepresented languages. And adapters these days also, or variants in this space, come in different forms and shapes. So different types of parameter efficient approaches have been kind of projected or framed in the same framework as adapters, and can be expressed as simply different variants that kind of tune or modify different knobs in terms of the model design. So whether an adapter is kind of applied sequentially or in parallel, or whether you include a scaling factor or not compared to the original adapter. And so I think there's going to be kind of a lot of interesting work as well in terms of designing different adapter variants that are maybe particularly useful for different downstream settings. And finally, as an additional form, kind of going beyond this setting of it, adding additional parameters to the model post hoc, there are also ways in which you can use in which you can allocate additional language-specific capacity that is already available within the model. And one particularly interesting and promising line of research here is to use methods similar to lottery tickets to identify useful or salient subnetworks that are kind of very highly activated for different languages or for different tasks, and then to just train those particular sparse subnetworks. And the very nice property of these subnetworks as well is that they can then be combined and composed. So here, for instance, in this figure below, you can compose a subnetwork that you've learned for language as well as a subnetwork that you've learned for task, again, to do zero-shot transfer in this new previously unseen language-task combination. So in general, takeaways from this section, I just want to highlight again here adapters as I think a really useful and practical method to allocate additional language-specific capacity very parameter efficiently. And as I've hopefully was able to show, they can not only improve performance, but also have other benefits like improving robustness and sample efficiency as well. And beyond that, I think they're really useful in that they can be flexible, and generally language-specific capacity can be allocated or used in different forms. And beyond that, if you're kind of interested in using adapters, there's also this adapter hub, as well as a number of other libraries that you can use for training these parameter-efficient multilingual, monolingual models. Now, just coming to the last part of the talk, I'm kind of also looping back a bit to the subword segmentation of some of the limitations that I mentioned about subword segmentation initially. So instead of trying to improve subword segmentation or modifying the subword segmentation algorithm, we could instead decide to discard the subword segmentation algorithm completely and just consume the input byte sequence of the of any language or of our data directly. However, kind of naively applying a transformer stack to the input byte sequence results in quite a lot of increased computation due to the increased sequence length of consuming the bytes one by one, which is particularly problematic given the quadratic complexity of attention. So as an alternative, we propose here, and this is joint work with Yi, Win, and a whole host of other collaborators. We propose here kind of a soft way to learn a soft subword sequence, basically in a gradient-based way directly from the data that we can then use to instead of our original subword sequence. And the method here consists of a couple of different steps. We originally have our byte or character sequence, and then basically enumerate all our possible subword blocks with different block sizes. So for instance, if we consider blocks up to size 4, we enumerate here our possible blocks of size 4 here. And then for each block, we obtain a block representation simply using a strided pooling function. So by just doing mean pooling over each specific block, we pool the representations of our characters or bytes here, for which we learn embeddings, into a joint block level representation. Now with these block level representations in hand, because these are now on the block level, we again kind of replicate them so that they are nicely aligned, so that each 1 block, 2 block, and 3 block is kind of aligned with regard to the corresponding blocks at each character position. And we now apply kind of this another block scoring network at each case to learn a score for each block at every position in our model. So basically, this block scoring network essentially learns how important or how relevant this particular subword block is at this position for the overall representation or performance of the model. And then, because now from this block scoring network, we are getting absolute numbers, we are simply applying a softmax transformation at each position to make all of these block scores at each position, again, relative. And then finally, to basically compute what we call here our latent subwords, we're essentially taking kind of each position here. We're basically summing the corresponding block embeddings of each subword blocks at this position. So here, the corresponding blocks of the 1 block, 2 block, 3 block, and 4 block subwords, and then weighted by the block score that we've learned in the previous section. And as a result here, now based on that, we basically get from all of these different possible combinations of subwords, we again get kind of a single sequence of these individual latent subword representations, basically at every position of each original byte. However, just using these latent subwords now, we're basically still having kind of the same issues of inefficiency as before, as the model would still need to consume every latent kind of subword itself. So now again, we apply kind of a separate, again, mean pooling operation, where we, with a given stride, kind of pool all of the latent subwords into kind of a much smaller scale, so that using kind of factor of 2, for instance, we're left in the end with a sequence that is about half as long as the original one. And by doing that as well, we are kind of getting rid of or taking care a lot of like overlap or redundancies, as you may expect, between different adjacent characters or bytes, for instance. The other aspect, so this is the kind of soft gradient-based subword segmentation algorithm. But the other aspect to consider when comparing the subword-based models with byte-based models is how they allocate their parameters. So typically in multilingual subword-based models, most of the parameters are actually allocated to the subword embeddings, because they multilingual vocabulary is up to 250,000 tokens large. So much of the capacity of the model is actually spent just on modeling words or subwords in its representation space. Consequently, for character level models, we have much less, as we are only having embeddings for particular characters or bytes, we actually have much less capacity or much less space in the embedding space allocated to these models. So to make up for that, we can allocate some of the additional capacity to the encoder, to make the encoder deeper, basically, and give it more capacity and flexibility to learn word level representations that might otherwise be learned by the embeddings in subword-based approaches. So now, just for the evaluation here, I just want to show a couple of numbers. So in the paper, we compare to both monolingual as well as multilingual approaches. But here I'm just showing results on some multilingual benchmarks for different multilingual tasks against kind of a very strong multilingual method, multilingual T5, as well as against kind of the directly applying a T5 style model directly to the byte level sequence. And as you can see here, our character, so the K-former model, outperforms both the byte level model across the different tasks and achieves performance that is kind of similar and on par to the subword-based multilingual T5 model. However, with much fewer parameters. And so we do not need to consume these large embedding parameters like in the subword-based model. And as I was talking about the benefits of time efficiency as well, you can see here kind of a comparison of the different factors like the speed or the memory or the floating point operations of the model. And interestingly enough as well, similarly to the kind of reduced parameter size and to the improved or similar performance, the K-former, so using this soft subword segmentation, is about twice as fast as directly applying a model to the bytes directly, and also about twice as fast as the subword-based T5 model as well. So by moving from characters or moving from subwords to characters or bytes, we not only save in parameters, but we can also actually improve and make our models faster. So with that, just want to say again that I think these days, given kind of recent advances in pre-training and in modeling developments, byte models or character-based models are actually really competitive with their subword-based counterparts. And in particular, particularly for settings where models have to deal with a lot of noise, whether it is synthetic or natural, so from both social media type domains, or particularly for low resource languages. And coupled with appropriate downsampling and scaling of the encoder, byte-based models can actually be faster and have both fewer parameters than their subword-based counterparts. And beyond that, I think byte maze or models, or just simply getting rid of the subword segmentation algorithm has many other benefits, like increasing robustness to different forms of noise, or leading to better performance in low resource settings. So with that, just want to end here again, highlighting these 3 dimensions of efficiency that I mentioned, and kind of mentioning again, as I already touched upon a couple of times throughout the talk, in general, I think it's really useful not to think of these dimensions really in isolation, but they typically kind of influence or help each other in that improving, for instance, space efficiency might also lead to improved sample efficiency, like with adapter-based approaches, or space and time efficient models are typically tied together as well. And generally, I want to kind of end here with just encouraging using efficiency, not only as an evaluation, but also as a model design criterion, because I think this focus of efficiency and kind of on Occam's razor simplicity in modeling design, or more simplistic hypothesis, can really lead to improved robustness, particularly in the phase of really low resource settings, and ultimately to improve performance and improve generalization as well. So with that, thanks a lot for your attention. Thanks for inviting me. And I hope you all have a fantastic workshop and a fantastic rest of the conference.
Thank you, Sebastian. We have time for maybe a couple of questions. No. Is the mic turned on? No. Yeah.
No? Okay, now it's working. Great. Thanks a lot for the very exciting talk. I'm Eric Malmi. So I was wondering, it seemed to me that most of the results you were showing were on NLU tasks. So do you know, or do you think the gains would generalize to generative tasks, or for instance, machine translation?
Thanks. Yeah, I think that's a great question. Yes, I think you're right in that most of the results I mentioned were on NLU tasks. So for adapters in general, they have also been, or some of the earliest applications of them for NLP have actually been for machine translation, particularly for very multilingual machine translation systems, which often also struggle with similar problems to these multilingual models, where it can be difficult to allocate additional capacity for each language. And and recently there have been a couple of interesting directions in the multilingual, like machine translation setting as well. For instance, using or allocating specific capacity for specific language directions in particular. And and I think in general for these types of for generative approaches or for machine translation, I think particularly in the larger scale settings, I think having some like conditional capacity or like allocated capacity can be really useful. In the recent Facebook paper, for instance, where they scaled to about 100 languages, I think one of the crucial points was also there having this sparse mixture of expert layer or model that can kind of adaptively allocate different capacity for different languages or different settings. So I think this kind of methodology is hopefully more general and relates to different NLP tasks.
Thanks a lot.
Yes, I can ask one more question. So a lot of the methods that you presented today, they were really cool from a technical point of view. But is the understanding correct that for truly low resource languages, some of these methods will need like extreme expertise to be implemented, or are some of these methods actually applicable for truly low resource languages where the researchers may or may not have access to complex computational systems?
Yeah, I think that's a great question. I mean, in practice, I guess, most of the methods I mentioned, so both the adapter-based methods as well as kind of these character-level models, still rely on sufficient amounts of multilingual data for training models. So the only methods I really mentioned that are, I think, potentially useful in these very limited data settings are these data augmentation methods, using things like building lexicons to augment or to get additional data for settings with that, like simply unlabeled data is rarely available, available in a really limited quality. So I think in general we can do, I think on that side, really trying to procure and obtain kind of more high quality or simply more diverse sources of unlabeled data is something that has like trickle down effects that can enable a lot of other approaches, but also developing methods that can learn very well from very limited or even like a few thousand sentences, and that can already learn like the syntax or the like morphological relationships. And I think there in particular, maybe incorporating more like linguistic expertise as well, really trying to learn as much as we can linguistically from like a few, like learning word formation and other types of like semantic or syntactic rules from very few data, incorporating that knowledge back into models, I think is really, really promising direction.
Yeah, fingers crossed. Thank you so much again for the wonderful talk, Sebastian.
Thank you.
All right, now is the time for the first of our two spotlight papers. The first paper is pre-training data quality and quantity for a low resource language, new corpus and BERT models for Maltese, which will be presented by Kurt Mikulev from University of Malta. So Kurt, please come over.
Hi. I'd like to first start by thanking the organizers for choosing this paper to appear as a spotlight talk. So I'm Kurt, and I'm proud to be here presenting our work, which is titled Pre-training Data Quality and Quantity for a Low Resource Language, New Corpus and BERT Models for Maltese. So in the talk, it will be split as follows. I will start by giving a brief overview. I will present the new corpus and models which are part of this work. I will then show how we evaluated these models, and lastly, finish off with an in-depth analysis. So starting from the background, as we all know, large pre-trained models have become a core component of many NLP scenarios due to the state-of-the-art results that they achieve, but also in that they are relatively inexpensive to fine-tune. But of course, they are only available for a number of languages, which is where multilingual models come into play. And these models have shown impressive cross-lingual transfer capabilities. Despite this, the curse of multilinguality limits the language-specific features that the model can able to learn, and tends to disadvantage the lowest resource languages in such models. So in this work, we focus on Maltese, which is a language spoken primarily in the country of Malta, as well as smaller communities around the world. It is an official EU language, and it is the only Semitic language written exclusively in the Latin script. So apart from the Arabic influences, it also has extensive lexical borrowing from Romance languages such as Italian, as well as the English language. In the context of NLP, it is a low resource language, and it is not part of either BERT or XLMR. Furthermore, a recent work has shown that for Maltese, further pre-training multilingual BERT on the language is beneficial than using BERT out of the box. And in fact, this is a technique that we make use of in this work. So I will now present the new corpus, which we call Corpus Multi version 4. It is in fact a continuation on the previous version. It is roughly twice its size at just under 500 million tokens. Rather than doing opportunistic data crawling initiatives, we collect the data from specific sources. Admittedly, this results in less overall data, but we argue that the resultant corpus is of a higher quality and less noisy. We also keep the data split into 19 different domains and genres, and one of this domain is in fact the Wikipedia domain, which is extensively used, especially in the low resource setting. However, Wikipedia is in fact less than 1% of this entire corpus, and from a few megabytes, Corpus Multi amasses around 2.5 gigabytes of data. Admittedly, this is a substantial increase in data, but I still have to stress that Maltese is by no means a high resource language. And this is especially evident when you compare larger models and the corpora that they use, which are magnitudes larger than what we have in this work. Despite this, we still set out to pre-train our new language models, which we call BERT2 and MBERT2. So what these are, MBERT2 is a monolingual model pre-trained from scratch using the BERT-based architecture, whereas MBERT2 is a further pre-trained multilingual BERT. For the latter, we also use the vocabulary augmentation technique from previous work, where we replace the 99 unused tokens, which is present in the multilingual model, with multi-specific tokens. I will now present the evaluation, and consistent with many low resource works, we include the following morphosyntactic tagging tasks. However, we also felt the need to also include the semantic tasks to be able to compare the differences between syntactic and semantic tasks, which is why we included sentiment analysis as a further baseline. As for baselines, we include multilingual BERT, and we also include two special versions of BERT2 and MBERT2, which are only pre-trained on the Maltese Wikipedia portion of the data. And we call these BERT2 Wiki and MBERT2 Wiki. So starting from the baselines, we see that the MBERT2 Wiki models at this low resource level typically performs better than the BERT model, and multilingual BERT without any further pre-training performs somewhere in between. The only exception to this would be the named entity recognition task, which we will give a justification of why BERT Wiki performs slightly better than MBERT in a couple of slides. But looking further at our models pre-trained on Corpus Multi, we can see that both models perform consistently better on all tasks than the baselines. In fact, BERT is the best performing model on average, and the largest gains are seen in the sentiment analysis task with upwards of 20 F1 points. And this is the first piece of evidence that the language-specific embeddings are more suited for the semantic tasks. I will now provide two types of analyses, starting with how different pre-training domains has a bearing on the downstream performance. And we do this by taking the BERT Wiki and MBERT Wiki models from the baselines, and we compare them with with two new models, which we call BERT mixed and MBERT mixed. And what these are essentially are models which are pre-trained on the same number of sentences as the Wikipedia data, but we sample the sentences from the Corpus Multi, thereby achieving a mixture of domains. Other than that, is the same pre-training and fine-tuning procedure. We also compare with multilingual BERT, which is represented by the dotted line, and since we don't do any further pre-training, it will be constant in both scenarios, but it will act as a baseline of sorts. Starting, in fact, with the named entity recognition task. As I alluded to earlier, the BERT Wiki model proves to be a more competitive baseline than we had initially thought, whereas mixed pre-training is actually detrimental for this task, And this finding makes sense since the wiki and dataset that we make use of for this task comes from the Wikipedia domain. However, for the other task, mixed pre-training generally improves, though for dependency parsing and part of speech tagging, it is not as evident. But for sentiment analysis, this is in fact substantial. It is the improvements are so pronounced that BERT to mixed performs not only better than multilingual BERT, but also even better than MBERT to wiki, which goes to show how important it is to use carefully curated pre-training data, either by matching directly the pre-training domain, if that's available, or else using higher quality data from a mixture of domains. I will now present another type of analysis which has to do with the pre-training size. And we do this by taking the BERT2 and then BERT2 models, which are pre-trained on all of the data, and we gradually decrease the data proportion and pre-train new models as we go. We go as much as the BERT2 mixed and then BERT2 mixed models, which I have presented in the previous analysis. And for reference, these use just 0.38% of the data. Then we end up with a bunch of language models, which we fine-tune all of these on the target tasks. And as we can see from these visualizations, generally the performance improves with more and more data, although with diminishing returns as more data is added. Interestingly, with just 10% of the data, the performance improvement is quite substantial, so much so that the performance gap between the BERT2 and then BERT2 models is drastically reduced from what we had seen at 0.38% of the data. In fact, with 10% or more of the data on the sentiment analysis task, the monolingual model actually performs consistently better than the multilingual model, which is further evidence that the language-specific embeddings are better suited for the sentiment tasks, the semantic tasks. And the main takeaway here is that the amount of data needed to achieve considerable improvements does not need to be overly ambitious. To conclude, I have presented a new corpus and language models for Maltese and shown that these achieve state-of-the-art results in the 4 tasks. I have also presented an analysis of how the pre-training domain and size has a bearing on the downstream performance, and we hope that these insights encourage further work in Maltese as well as other low-resource languages. Finally, we make this new corpus and language models publicly available on the Hugging Face Hub, and I encourage you to use them and experiment with them. And with that, I'd like to say grazie tal-ħin ta'kom. Thank you for your time.
We'll actually have to move on to the second talk.
Thank you.
Please ask Kurt your questions in the coffee break. So our second talk is by Derek Chen from ASAP Technologies, and he'll be presenting his work on Clean or Annotate, how to spend a limited data collection budget.
Great. Hello, everyone. Okay, good morning. My name is Derek Chen. I'm from ASAP. I'll be presenting Clean or Annotate, how to spend a limited data collection budget. This is joint work with Zhou Yu from Columbia University and Sam Bowman from NYU. So to give a little bit of motivation for this work, we look at a typical machine learning pipeline where we see that we start with a bunch of data, we feed that into a model of some sort, we train that model to get a bunch of parameters, and then we profit. Well, typically it's not that simple, especially when we want to deal with real world constraints, which are typically low resource. Oftentimes we look at things from the model perspective, but in our case, we're going to look at things from a data-centric approach. So in particular, we note that oftentimes when we're trying to get data for our models, there's actually quite a bit of work involved. You have to create guidelines to work with the different types of annotators. You have to actually do the annotation and labeling itself. There might be some sort of quality assurance work to make sure that the labels are clean, and then you have to organize and pre-process it. In other words, this can actually be quite a resource-intensive process. So what do we want to do about this? When we think about this in a typical setting, what we really want is to be able to get data that is both high in quality as well as high in quantity. But this might not be that straightforward. If we take the default labeling approach, what we're going to do is we're going to suppose that we have a budget of 12,000 available annotations. In this diagram, we have the number of columns, which refer to the number of examples that we're allowed to annotate, where each block represents 1,000 examples. And the number of rows is the number of passes that we have for each annotation. In the default setting, we simply just take the 12,000 annotations and we annotate 12,000 examples. This is very straightforward. Within the spectrum of quality and quantity, it's basically somewhere in the middle. So we treat this as our control baseline. But then what if we wanted to actually move towards higher quality? Well, a typical way to do this is to do something like a majority vote. So going with our same 12,000 annotations, what we might do is take multiple passes and say that we only keep the label that is actually a majority vote of what the annotators say. Now, this is great, but there's a drawback. And in particular, when we look at the spectrum, we now have higher quality, but this comes at the expense of having fewer labels. All right, so if you have fewer labels, maybe the model doesn't actually train as well as you would want it to. Well, is there something at the other end of the spectrum where we're still allowed to have more labels? Well, the answer is yes. A number of researchers have worked on various forms of denoising algorithms. In this case, you're allowed to take full advantage of the full set of annotations that you have available. And the way that you achieve quality is instead by having different techniques that allow you to clean up the data in some sort and remove the noise that you had when you did everything in one single pass. This type of denoising techniques can come in three general categories. The first way is to model the label noise in order to remove it. There are techniques here such as using a noise transition matrix in which you map out the relationship for each noise of classes, and then during inference time for any given noisy prediction, you actually revert it based on the mapping to get the clean label. There's also other ways of loss correction. The second category is to create a robust loss function that is less susceptible to noise. So in other words, maybe we can somehow modify the loss function itself as we're training the model. These include methods such as regularization penalties that say, hey, don't pay too much attention to any given example, or within the loss function itself that minimizes the impact of any single noisy example, while hopefully still allowing you to learn gradients from the clean examples. A third category is to manipulate the examples themselves. And so what you can do here is you can say, if I can somehow tell which examples are noisy, maybe I can filter or remove them. I can maybe use some sort of extra model or the same model itself with pseudo labeling to relabel those examples so they go from noisy to clean, or I could lower the weight proportional to the likelihood of noise of that example. Now, these are all great, but they still, these are all great. And within this spectrum, we're able to then get more quantity and hopefully still higher quality. With all of that said, there are still some key shortcomings with these sorts of denoising techniques. So in particular, basically all of them require training extra model parameters. There's extra model components that come into play. And to the extent that we're really trying to keep things in a low resource setting and considering practical concerns, whenever we're trying to deploy something into production, even the smallest amount of extra modeling creates extra code complexity as it has to go through QA and other types of processes, such as system maintenance over time. And finally, a lot of these types of denoising methods were developed in the computer vision space and really work mainly in classification settings. So we ask ourselves, is there something that perhaps can strike the balance between these two extremes, but is also additionally easy to use as well? And so this is where we introduce our methods of data cleaning. And so how does this work? It turns out this is actually quite simple. All we're really doing is cleaning the data through targeted relabeling. And this comes in three basic steps. The first step is that you pre-train a model with a subset of your data. right? You're saving part of the annotation budget for later. Now, given this pre-trained model, you then identify the examples that are most likely to be mislabeled. Over here, it's columns 2 and 4. Finally, you use the remaining portion of the budget to annotate those specific examples. And because you're using human annotation as your remaining budget, now your entire data set is actually quite clean. And because you've already annotated quite a few examples, you also have high quantity of data as well. Now, one part I haven't mentioned, though, is how do you actually identify examples that are likely to be noisy? So I'm going to talk through this now. One thing I'll mention is that this is just a general problem. There's many ways to do this. In the paper, we offer 4 different methods, but for the interest of time in this talk, I'm just going to talk about 3 of them. The first one is going to be called area under the margin. The way that this works is that we'll feed each example into the pre-trained model to obtain some sort of distribution. And so in this figure here, we see that there's some number of classes, and then there's some output probability associated with each class. Then we find the margin between the probability assigned to the target label and the next highest class that is not the label. So the difference between these 2 classes is going to be considered our margin. Now, when this margin is large, that means that the model is confident of its prediction. In contrast, when this margin is small, that means that the model might not be so confident, and therefore the example itself might be noisy. Then it becomes a candidate for removal or relabeling. Now, a second method is to look at prototypical clustering. The way that this one works is that we first embed all examples into some shared space. Right, it's just a bunch of, you can feed this through BERT or your embedder of choice. As a second step, we will cluster all of these examples by their label. Those labels might be slightly noisy, that's what we're trying to clean, but they should be relatively correct. The next step is to then calculate the cluster centroids for each of those groups. And then that's how you get that point in the center. As a final step, you simply look at each data point and compare that data point to its given centroid. So we're comparing the green to the green, and we're comparing the blue to the blue. Now, in the cases where that data point is far away from its centroid, that means it's kind of like an outlier, and therefore that might actually be mislabeled and therefore is noisy and should be relabeled. Finally, a last method that we consider is the large loss technique. This one is quite simple. All we do is we run the examples through the pre-trained model, and the examples with a large loss are candidates for cleaning. The intuition behind this is that with large neural networks these days, they're actually quite powerful, and they're even able to completely memorize random static noise. But when it does something like this, it tends to learn the clean examples before moving on to the noisy ones. And so in this case, what we'll do is we'll train the models for some period of time. And then by looking at the dev set results, we'll say, hey, when is it starting to overfit? At that point, it is likely has learned the clean examples, but not the noisy ones yet. So the noisy ones will still have a large loss. Then therefore, the examples that still have a large loss are the ones that we might want to relabel. So putting all of this together, we are now going to talk about the results. Getting into this chart, we'll start at the the top couple of rows. We've already talked about the control, which is kind of our default labeling method, as well as the majority vote. We've also included an oracle, which says that what if we had all data available and everything is multiply annotated and it's just super perfect. It's kind of our upper baseline. Our second grouping is the denoising methods that I kind of mentioned. These are some specific ones. They're all actually fairly novel to apply to the NLP space. And then lastly, we have our cleaning methods with the different ways of identifying errors, including large loss, area under the margin, dataset cartography, and prototypical networks. And then on the column side, we have different types of models. And so in particular, we have things that are relatively small, such as a quick, simple, fast text model. We have a medium-sized one, which we're using as a distilled Roberta. And we also have a large one, which we use as a DeBerta X large. So what are the actual conclusions? Well, the first thing that we really notice is that the majority option tends to do the worst overall. This particular chart talks about sentiment analysis, but we actually cover multiple tasks and multiple types of tasks. And across all of them, majority just always doesn't do quite as well. And so what this means is that even though you want to have high quality, if it's coming at the expense of super, super low quantity, that's really just going to hurt you quite a bit. And so that's not really what you want to do. On the other hand, the denoising methods tend to lose out to what actually comes out, which is our cleaning methods over here. And the cleaning methods are pretty much always either on par or better than the more complicated denoising algorithms. And in particular, this is the best part, one of the best cleaning methods actually turns out to be large loss. And this is actually amazing because large loss is actually one of the easiest ideas to really implement in practice. And if we especially think about low resource settings, this is really what we're aiming for. And so what does that really mean? If you really want to have this good balance of clean, but also high quantity data, all you have to do is follow this like simple process. What you do is you pre-train a model with part of your budget. It's a model that you already have and you're already going to build. You find out which ones the model gets wrong and you say, let's go fix those. And that's it. It's just those 3 steps. And so with that said, if you would like to look at more details, please check out the paper on arXiv, where we dig into more things like different NLP tasks, ablation studies on each component, and answering questions like what proportion of the data annotation budget should be used for pre-training versus cleaning. And finally, as an alternative, please come visit me at the in-person poster session. Thank you very much.
Once again, we'll take the questions at the poster session for Derek as well. So this concludes the first part of our workshop today, and we'll be breaking for coffee now. And we'll see you all at, say, 10:35 for our next invited speaker. Thank you. All right, welcome back to DeepLo. We will start with our next invited speaker, and it's my delight to introduce David Adelani from Saarland University. So David is a doctoral student in the computer science department at Saarland University and an active member of the Mazakane NLP, a grassroots organization whose mission is to strengthen and spur NLP research in African languages for Africans by Africans. His current research focuses on NLP for African languages, multilingual representation learning, and privacy in NLP. You might have already seen his work on African news at this conference. So without further ado, let's have David on stage.
Thank you very much for the introduction. Now I have to look for my slide. The slide is not showing. Yeah. Okay, thank you very much. Yeah. Okay. Yes. Okay. Thank you once again for the invitation to give this talk. And a big thank you to the organizers of DeepLo. Today, I'll be talking about multilingual adaptive fine-tuning, a study on African languages. And I'm David Adelani from Zalan University. So this work is based on an African NLP workshop, which is called Multilingual Language Model Adaptive Fine-Tuning. And it's in collaboration with my colleagues, Jesu Joba, Marius, and Dietrich, who's also my supervisor. So first I want to talk about, I will start the discussion with pre-trained language models. And you know that the size has been increasing every year. And also apart from the size being increasing, also the performance is getting better. But it's also often difficult for low resource communities to run this model and to actually benefit from the power of these pre-trained language models. But the interesting thing is that we also have some very clever self-supervised techniques that have been developed alongside, for example, the way BERT was trained is quite interesting using Mark's language model, and also the way T5 and BERT has been trained. So there are a lot of things to learn from all this. So the most interesting thing to me is because these models, we also have multilingual variants of these models. But the problem is that it's really difficult to cover all the 7,000 languages. So today I'm just going to share what I've learned in the last 2 years based on the challenges of working on low resource NLP and low resource languages in general. So let's look at the challenges. I think the first challenge I want to talk about is the problem of inadequate evaluation data set across languages. Because you could claim that this model works very well and works on English, Spanish, German, and which are kind of languages from the same family, and they're kind of related. So what about a distant language like isiZulu, which is spoken in South Africa with a lot of morphology? Will it still work? So of course, it's difficult to evaluate on 7,000 languages. There have been ideas of evaluating on typologically diverse languages, for example, on the Extreme benchmark, which already covers like 50 languages, but just 4 African languages: Afrikaans, Swahili, Wolof, and Yoruba. So, but if you look at the evaluation data set, most of the time, for many tasks, the languages that are being covered are often less than 20 languages for most of the tasks, except for part of speech or anyhow. So that means we do not really understand how most of these models work very well on low resource languages. And here, the second challenge we have faced, especially while working with some African languages, the problem of scripts. So covering many scripts is very important because we have over 100 writing scripts in the world. And if your model is only biased to the Latin script, for example, like the multilingual BERT, and most of the languages use the Latin script, and languages like Amharic was not covered, even though they were represented on the web. And so the subword is kind of biased to Latin script, and also the model fails to work on languages that the scripts have not been covered. So another one is cost of dimensionality, which also a lot of people have talked about during the conference. Even there's a paper on lifting the cost of multilinguality or dimensionality, and which the cost of dimensionality is just a trade-off between the language coverage and the model capacity. So if we want to cover as many languages, we have to also increase our model capacity, which is often difficult because it's difficult to train. And also, we do not have a lot of available data set for many low resource languages. And another problem I'm interested in is that how can we really make this model smaller so that it's really easy to run by low resource communities. So in addressing this. I'm not just going to talk about the problems. I want to talk about how we try to address them. The first one is using the participatory approach by Masakani, where we collaborated with Masakani, a grassroots NLP community for Africans and by African. And the idea is we're pioneering this participatory research for African NLP, where we develop some evaluation data set in a very important task like name entity recognition. And this covers like 10 African languages. And name entity recognition, I'm sure most people are familiar with this. It's just a token classification task where you want to classify entities like personal name, like location, organization, or date. And an example is on the right-hand side where you have on the 4th of February, and you could label this as a date. We also have some special prefix that indicates whether this is the beginning of the span or the middle. So Global Voices is an organization and Fernando Gomez is a personal name. So for this task, our idea is to try to focus on creating name entity recognition data set for it. So first, let's look at the language characteristics. As you can see, if you translate this sentence, the emir of Kano, Toban Zhang, who has spent 18 years in Nigeria. So if you translate this to Amharic, you'll find a different script. And I think there was a talk on, was it on Monday or Tuesday, about one of the factors that makes cross-lingual transfer fail is script. So Amharic is script and word order. Amharic is using a different script and a different word order. It's using SOV, and the script is, of course, you can see is a GI script, which is very different. So just trying to do zero-shot transfer from English might be difficult. And also you have other languages. That, most African languages use this Latin script, mostly due to colonization, and people have been forced to write with the Latin script. So our focus languages are like 10 African languages. We have about 5 languages from West Africa, Nigerian Pidgin, Hausa, Igbo, Yoruba, and Wolof. And also from East Africa, we have Swahili, Amharic, Luganda, Luo, and Kiwanda. And here, the Swahili is also spoken in the DRC, which is in Central Africa. So although why do we need to create this? People often evaluate on WikiNN. We could just go ahead with this. But for African languages that are represented in WikiNN, most of the time they have like 1,000 tokens, which is not really good for training and evaluating the quality of these models. And WikiNN only covers few African languages, I think like 4 or 5. So we need to expand this. We have Sadila, that is created for 10 South African languages, or 11 South African languages, but it's based on the government data, which doesn't generalize to several domains. And the last one is this Lorari, which was, but this one covers more African languages, but it's not publicly available, which is quite difficult that you have some named entity recognition data set that is behind paywall and African researchers cannot use it. So we decided to create Masakana, which is open source and also has very high quality. So it has been annotated in a participatory manner by native speakers, and we have very high inter-agreement score. And each sentence has been annotated by a minimum of 2 annotators. So this is the data set. From the data source, it's mostly from the news domain. Most of the time, it's, the size is from about 2,000 to 3,000 sentences, which we have split into training, development, and validation. And you can see that most of the time, we have more than 10% of the tokens are entities, which is very good, except for Wolof, which do not have so many entities. So for the baseline models, we evaluated on CNN by LSTM CRF model, which is very popular model before the pre-trained models. And we also fine-tuned pre-trained language models like Multilingual BERT and XLM Roberta. So Multilingual BERT and XLM Roberta only cover a few African languages. Multilingual BERT cover like 4 African languages, like Afrikaans, I think Afrikaans, Malagasy, Yoruba, and Swahili. And the SLM HAR covers, I think, about 7. But in our targets data set, only 2 or 3 have been covered. So for the baseline models, first I want to also highlight the importance of script. So if you train Amharic on multilingual BERT, you are going to get like an F1 score of 0. In general, these pre-trained models, they perform better than CNN by LSTM model, but if the script is not supported, it doesn't work. So except you do some adaptation based on the script. So for Hausa, because it's been supported, so Hausa is supported in the XLMR, but not in MBERT, so we gave slightly better performance. The same thing applies to Yoruba. MBERT supports Yoruba, and XLMR does not support Yoruba, and we have slightly better performance using multilingual BERT. So, but on average, if you exclude Amharic, actually, it doesn't seem that there's a big difference there's no difference between MBERT or XLMR. So the second problem we try to address is how do we address the limited language coverage? Because of course we want to add as many more African languages as possible. But we are faced with this cost of dimensionality problem. And here also this inadequate pre-training corpus, so we cannot pre-train from the scratch. So here we do language adaptation on the pre-trained language model. So we employ 2 methods. The first one is we can employ 2 methods. One is language adaptive fine-tuning, where we fine-tune the pre-trained language model on a monolingual corpus of that language using the same pre-training objective. And this has been shown to work very well for a new language or for a new domain. The second approach would be language adaptation in the framework of parameter efficient fine-tuning. So Sebastian talked about the adapters today, so you could also do language adaptation and also the sparse fine-tunings. So for the language adaptive fine-tuning, what you have to do is that you start with the initial model, multilingual BERT, that has been pre-trained on the languages, and you could initialize the weights and continue pre-training on a new corpus, for example, Yoruba, and you have a Yoruba BERT. And after that, we use the same objective, like from multilingual BERT, basically you try to predict the mass tokens. And then you can now fine-tune on the target task, Yoruba NER. So from the results, what you can see that just direct application of LAFT is very helpful. And you can see in most cases, which is the one on the lower side, you will find out that we could improve regardless of the initial pre-trained model that we use. The interesting thing, for example, is Hausa. If you do language adaptation on multilingual BERT, although multilingual BERT doesn't support Hausa, you find out that there's no difference again between MBERT plus LAFT and XLMR plus LAFT. The same situation applies for Yoruba, although multilingual BERT has seen Yoruba text. If you do language adaptive fine-tuning using XLMR, you actually have slightly better performance. So this approach is very good, even for languages that are not supported. But the script has to be supported. As you can see here, the Amharic, if you do language adaptation, you still have F1 score of 0. So how do we address this problem? We could address this non-supported script problem by doing vocabulary replacement. So this is very simple, where you just replace some or all the embedded vocabulary by a new vocabulary, which is from Amharic. This is very simple, you just replace vocabulary. And then you can apply LAFT. So here you might want to apply it on very small learning rate. The second one is vocabulary augmentation, which allows you to add new tokens, and you can still preserve the initial vocabulary. And for example, Chow recommend adding 99 new subword units for a new language. But when the script is not supported, you might actually need to add like more tokens. So this is an experiment on these 2 approaches. And you can see that by this, we could improve the performance from 0 to 60 using this vocabulary replacement. But we find that doing vocabulary augmentation is actually better, slightly better, 2% improvement. But if you compare this performance to the SLMR based with LAFT, you see that there is still a large difference. So which shows that it's important that the initial pre-trained language model has seen so many scripts. So at least I think we can actually optimize for this when we are pre-training in the design, that we try to cover as many scripts as possible, because language adaptation might be harder. Okay, so first, now I'll talk about some of the limitations of LAFT. LAFT creates a copy of the pre-trained language model for each language. So it's very effective, but actually it also takes a lot of disk space and it's not parameter efficient. Also, it's very expensive to train for several languages, and also limits, once you have trained this, it limits the cross-lingual transfer because the model has been adapted for a new language, for example, Yoruba, and if you want to adapt to from Yoruba to another language, the performance drops. Okay, and it's also very difficult to adapt to non-supported scripts. Okay, how do we address this limitation? So in general, you could probably pre-train to cover more languages and several scripts, or use some parameter efficient approaches like adapters. So here for African languages, where we're thinking about this problem, we find out that actually we do cover just like two major scripts, Latin and GI script. And if you want to have some other languages like Arabic, you can also add Arabic script. And so when we also did some analysis of the corpus we have, we found out that we do not actually have a lot of big corpus for most of the languages. Only about 70 languages have over 50 MB of multilingual text. So we just like selected those languages, which is like 17 African languages. Then we added 3 languages that are widely spoken in Africa, English, French, and Arabic. Then we do what is called multilingual adaptive fine-tuning, where we are doing adaptation on multiple languages at the same time. So here we have a new model called Ifeoluwa, where we just initialize the weight and continue pre-training on new corpus that covers 70 African languages, including English, French, and Arabic. So here we try to cover like 3 scripts, Arabic, Latin, and GIS. And we've just fine-tuned this on 3 epochs. Okay, so the alternative is to actually pre-train from scratch. There's a paper called AfriBeta, which the idea is that can we actually learn a good multilingual language model from a small size corpus? And actually the answer is yes. They were able to train a multilingual pre-trained model on less than a gig of data for 11 languages and actually have very impressive performance. But they only focus on languages that are mostly from West Africa and East Africa. So the Southern Africa was not represented. So, but with the MAFT approach, we are able to quickly cover most of the regions of Africa. Some are still like missing, but most of the time we cover all the scripts and we have a language that is similar to those ones that are missing. So if we evaluate on MAFT, we evaluated on name density recognition and sentiment classification, which is coming from 2 corpus, Niger Senti that covers 4 Nigerian languages, and also we evaluated on Amharic and English. So for the evaluation on Masakana, you can see here that there's no much big difference between LAFT that you have to adapt on each of the language and MAFT, which is a single model. So we have, we evaluated on 12 languages. So this is having a single model rather than having 12 different models. And the performance difference is not actually a lot. So in most cases, it looks like the MAFT is still better, especially for Amharic. But I think for most languages, performance difference is just a little. So another interesting thing is that we see that we can still maintain the performance of English. That has seen a lot of, English is already good in the original HLMR. So after adaptation, we could still maintain the performance. So we also try to do that for AfriBeta. Instead of adapting XLMR, we try to see if we can adapt AfriBeta, which has already seen about 11 African languages, but it was actually very difficult to adapt. As you can see, the performance stays the same or even slightly worse. So this shows that we do benefit from using a very diverse and multilingual vocabulary of the XMR for when we do adaptation than using a vocabulary that has seen fewer languages. Okay. So we also evaluated on sentiment classification task, and as you can see, math is still very competitive, although we have sometimes that the left is still better, but we had the advantage of having a single model than having multiple ones. Okay. So, and in some cases, like the Nigerian pidgin, we find out that math is actually better than left. Okay, so now to talk about the third problem, which is how do we address the hardware restrictions of VLMs? You could have a very good model, but if it's difficult to run for people in the low resource community, nobody is going to use it. So one of the advantages of the AfriBeta is that it's smaller and people can actually run it on platforms like Google Colab. So to address this, we try to employ, there are several approaches. One approach would be knowledge distillation, where you can distill embeds, like to have distill embeds, or from XMR, you could also have this variant called M-mini. But here we are doing what is called vocabulary reduction, because the embedding layer actually takes most of the parameters of the model are in the embedding layer. So we see that if we can reduce the vocabulary there, we could actually make our models significantly more smaller, up to like 50%. So here, and this approach has been done for European languages. So if you your target language is just English, French, and Spanish, you don't need to use all the vocabulary for the remaining languages. You could just like reduce the vocabulary. And the performance most of the time stays the same. Okay, so we apply this approach for compression. So first we have to choose a multilingual pre-trained model that covers as many African languages as possible and as many scripts. Then we apply sentence speeds to all the monolingual text. And here we try different settings because Amharic was giving us some tough time, so we had to treat it separately at some point. And at the third step, we apply SMR tokenizer to all the text and selected the top K subword tokens. So we are able to reduce the vocabulary size from 250 to 70K, and thereby reducing the entire parameter size of the model by up to 50%. Yeah. So then we apply MAFT again, and this is the evaluation result. As you can see that from the XMR base plus MAFT and the XMR base vocabulary of 70K plus MAFT, that's the reduced version. You find that the performance difference is not a lot. And if we compare this to the distill XMR, we find out that we are able to do much better. Okay, so the distill XMR, which is called the mini LM, the performance drops by close to 5 points. Okay, so the second approach is to do parameter efficient fine tuning. And here you could, the idea is that for direct fine tuning, you often modify all the parameters of the model. And again, not reusable for a new language when it's fine tuned and it's not parameter efficient. So an alternative to MAFT would be just to do language adaptation, for example, MADX or sparse fine tuning. So for the MADX, what they introduced MADX, which is a parameter efficient way of adding an adapter in between the intermediate layer of the pre-trained language model. And this achieves very good performance with 1% additional parameters. And the approach is very simple. Basically, you first train a language adapter on this high resource language, for example, English, and you train a language adapter on the target language. For example, it could be English, it could be Yoruba, and you train a task adapter jointly on the language adapter of English and that of the task you're interested. For example, name recognition. Then you could now swap the language adapter and use it for zero-shot transfer. Okay. So the second approach would be to use lottery tickets pass fine-tuning, which is another idea that came out recently. The paper was presented at ACL 2022, and it is based on the lottery ticket hypothesis, which says that each neural model contains a subnetwork that is a winning ticket that, if trained again in isolation, can reach or even surpass the performance of the original model. And our idea is to actually find what is this winning ticket or subnetwork. So this approach, which is the idea is to find the winning ticket for each task and find the winning ticket for each language. Then you can compose them together, similar to adapters for zero-shot transfer. So this is our algorithm. So for example, if you initialize the weight, theta, and the first approach will be to first do mass language model adaptation. And once you have done mass language model adaptation from the initial pre-trained model, you are going to now analyze the weight of the model and select the top K that changed the most. So those are the most important aspects of your parameters for that task or for the language. Then you can now repeat the adaptation again, but only modifying the top K that changed the most. And then you can now take the difference between the new model you have that is based on the top K that changed the most and the initial pre-trained model. And you can do this for a different task and a different language, similar to adapters. So this approach, we find that to work pretty very well in zero-shot setting. So this is an evaluation on African languages. And you can see that in most cases, we are not trying to compare which is better between adapter and this other method, but you can see that the performance is very impressive. And most of the time you have F1 score of over 70%, except for Wolof. But how can we improve on this? So here we are thinking of two ways of improving on this. Initially, this evaluation was done on Multilingual BERT, which is not the best model. We have better models. So, and also there's a domain mismatch. Most of these models and language adaptation has been done for the Wikipedia domain. So the idea is that if we do language adaptation on the news domain, we can actually improve the performance. So there are two ways of improving this. Use a better model that has been trained on African languages, or try to do more adaptation on the domain. So, and here we try to see what happens when you do an adaptation on the news domain, even starting with Multilingual BERT, and you can see that we can significantly improve the performance, especially for Wolof. So most of the time we pay attention to how can we adapt to a new language, but we forget that there is also a big domain mismatch. Then if you also use a different pre-trained language model, because XLMR in most cases is slightly better, you can often improve the performance slightly. And in this case, except for Yoruba. Then we make use of our new model, which is called AfroXLMR, and we found out that we are able to even improve the performance better. So here I'm advocating for paying attention to both the language and also the domain to further improve the performance of adaptation. Okay, and if you compare this zero-shot setting with the direct fine-tuning on supervised training data set, you find out that we are not really far from what we are going to get if we directly fine-tune on XLMR. This is very impressive. And in some cases, zero-shot transfer, we could actually get better performance by gently adapting both the language and the domain. And this is the case for Wolof and also Yoruba. The case for Wolof is quite interesting because we can significantly do better. So in conclusion, we studied some of the challenges of developing multilingual portrayal language model for low resource languages, and such as inadequate evaluation data sets, and also talking about the challenges of different writing scripts, cost of dimensionality, and the difficulty of running this model by the low resource communities. And we also talk about the different approaches of addressing some of these challenges by like creating new corpus using a participatory approach, or doing vocabulary augmentation or replacement. And in the context of African languages, we introduced multilingual adaptive fine-tuning, where we adapted XLMR to 20 languages. And also we show that it's important to take into account domain when doing parameter efficient fine-tuning to further improve the gains on language adaptation. And for the last problem, we make use of vocabulary reduction by reducing the subordinates in the embedding layer. And we are able to reduce the parameters needed to train our model by up to 50%. So thank you for listening to my talk, and yeah, questions.
Thank you, David. And we have a question.
Yeah, thank you. A very interesting talk. I was wondering, like, specifically about the topic on the unseen scripts. I'm working on generations, even more a problem for us. But for the task that you are working on, name-native recognition, I wonder, like, why don't you just transliterate the text to English script? Because, like, on the example that you showed, some other languages, it also sometimes, like, they use English, but they still spell things differently. Like Nigeria was spelled differently in some other language. So maybe if you just do it for what was the script?
To transliterate.
Yeah, transliteration.
Yeah, so it's an approach that, so there are two, for example, in this paper by Chow, so he proposed two approaches. You can either do vocabulary augmentation or do transliteration. So, and both of them kind of work similarly. But for the Amharic case, actually, they do not have capitalization. So if you do transliteration, maybe you're still going to struggle with another problem of no capitalization, which will also impact the downstream performance for NAR. And actually, script is not a big problem when you are doing cross-lingual transfer. So it's not actually one of the biggest issue. So, because even if the script is not, even if the scripts are different, you could still do zero-shot transfer. But the most important thing is that that script is covered in the portrayal language model.
But even if it's not covered, you can still transliterate to English.
Yeah, if it's not covered, so it's better to actually, if you transliterate, then you have to do this every time. And for some African languages, for example, for Amharic, the tool is not that perfect to do this conversion.
It doesn't have to be.
Yeah, so, and also for Amharic, because I discussed with some native speakers, there's also a lot of problem with the way it's been written. Some believe most texts of Amharic are not very standardized, especially the ones written by foreign media, that they do not write it properly. So they actually have some tools to write the script properly. And then another problem is now transliterate, so which is like 2 steps. Mm-hmm. So I will still like stick to advocating that people cover more scripts, especially in the case of African language, just because we have very few scripts that are used on the continent. So we have just 4. We have Unko script also used in Mali. So it's very easy to create a model that covers all the 4 scripts in Africa. So then we can quickly solve the problem at once than bothering about transliterating or doing vocabulary augmentation, because at the end of the day, the performance is still not that good. Yeah. So.
Hi, David. I have a question. You spoke about the importance of language coverage and domain to the performance of the models. If you had to pick only one, which one would it be and why?
Can you speak louder?
Sorry. I said you spoke about language coverage and domain when it came to the performance of the models.
Yeah.
If you had to pick only one, which one would it be and why?
I will pick language because like the biggest gain is coming from having the language adaptation first, then you can further improve it by domain. Like as you can see here, for example, we already cover like more than 80% for language adaptation for Hausa. So the domain performance is just like slightly better. So,
Okay, thanks.
Thank you.
So in that same spirit, I have like one last question. Are you aware or are you working with people who are actively taking these efforts and applying them for maybe building tools that are part of products that people are using? Or what are the things that you're most looking forward to continuing in these efforts?
That's a good question. I don't know of startups or organizations that are using this directly. Maybe some big tech companies are already using it in some ways because the data set is open source and is useful for many tasks like question and answering and other downstream tasks. But in Africa, maybe some are using it, maybe not. I'm not sure. But it depends on the task. For example, work on machine translation, it's easy for people to pick this up and use it. And maybe other simpler tasks like sentiment classification or hate speech detection, because they also face this problem, maybe for elections and things like that. So I'm not aware of, I cannot give like concrete examples of this, and I hope this happens in the future and people pay more attention to this. But another thing is that we also have the desire to put Africa on the NLP map, right? That there should be more research on African languages, more focus on an evaluation on African languages. And if we don't like develop data sets and work on this ourselves, it's difficult to challenge us to do this, right? So that's another stronger motivation. Yeah.
Absolutely. Thank you for doing this important work, and let's thank the speaker again.
Thank you.
Right. So the next thing on the agenda is the virtual poster session, and I will hand over the microphone to my co-organizer, Shangren from USC.
Thanks to everyone. So this first poster section will be fully virtual. So if you go to the underline page of the workshop, you will find the Gathertown link. And then all the posters has been already in place, and the authors of the poster will also be online. So feel free to join the Gathertown now and browse around. So the poster section will be start from now to like 12:15, and then I will be around as well. The afternoon, the second poster section will be hybrid. So you will have both the in-person section on the 7th floor demo room and also on the Gathertown. And then back after 12:15, we will have the lunch break, and then coming back from the lunch, we will have our next speaker, Yulia. Thanks, everyone. Go ahead.
Can I clarify a question? So the posters, the online posters that will be in the afternoon, will we also see them now? Or will there be posters that are only online in the afternoon?
So all the posters for both sections, they should already be in place in the Gathertown.
Okay.
Yeah.
Cool.
And
so it's okay to just go on the physical section in the afternoon.
But the authors of the poster sections, they might only be in certain sections because of the time zone difference.
Yeah, of course. Yeah, not everyone can.
Thank you. try it out. You can try it out.
And where should I point it? This laptop?
Yeah, this one. This is the next. Yes.
And back.
This is the back.
Okay.
Okay. But it's a little bit half-second delay. So if you click it, if it goes slowly, just wait a little bit.
No, didn't work. Okay. I just saw she struggled with slides so much during the talk. So.
Yeah, I think we all see.
Yeah.
Hello. Cool. All right. Welcome back for the afternoon part of the DeepLo, Deep Learning for Low Resource Learning workshop. I'm Xiang Ren. I'm a faculty at USC. So I will be introducing you to the next couple sections of the workshop. So it's our real great pleasure to have Yulia Tsvetkov from University of Washington to be giving a talk about her recent works on weak supervision for low resource NLP. So Yulia is an assistant professor at the computer science department at UW. Her research group works on computational ethics, multilingual NLP, and machine learning for NLP. So this research is motivated by the unified goal, which is to extend the capability of human language technology beyond individual populations and across language boundary, and thereby making it available to all users. And before joining UW, Yulia was an assistant professor at CMU and a postdoc at Stanford. And she'll be introducing and talking about interpretation as weak supervision for low resource NLP. Please take away. Welcome.
Thank you, Sean. All right. Hi. Thank you for inviting me. It's a pleasure to be here. Thank you all for attending my talk. I appreciate that you actually came to my talk rather than walking around in this beautiful city, in this beautiful weather. So I hope make it a little bit useful. So what I'm going to talk today is on interpretability. So when we talk about, this is a workshop on low resource NLP, and when we talk about low resource NLP, we typically always start our story with the fact that there are 6,000 languages, right? And there are a few resource rich languages, and there is like a few dozen medium resource languages. And then there is a long, long tail of thousands of languages which are resource poor, which don't have sufficient resources. And this is a huge motivation to this workshop and a lot of research in our area. So after looking at the list of presenters, other keynote speakers at this workshop, I realized that I'm collaborating with 2 out of 3 of them. So I decided not to overlap with them in terms of talking about my prior research on multilingual NLP. And instead, I will be talking about interpretability. Specifically, how can we use approaches to interpretability to facilitate low resource NLP, to improve generalization in low resource scenarios. And the motivation to use an interpretability is the fact that and of our current paradigm of how we use almost infinite data, but then train a static model, it does not kind of respond to the observation that language is very dynamic, that language is alive, that it's constantly changing, that there are domains that are constantly kind of have a constant flow of new information with new entities, new constructions, new dialects. And once we train, no matter how big our model is, it becomes static, right? So it's hard to accommodate the model to emerging patterns in data. So there are always low resource domains. And the question is how to adapt existing models, no matter how large pre-training data is, to such emerging domains for which we don't exactly know what will be next important entities or events, or those for which we don't know what will be adversarial attacks in the case of malicious usages. And there are kind of many scenarios, including in multilingual NLP. So for example, when I started this talk about 6,000 languages, obviously we don't need, it's not true that only 6,000 languages, NLP systems that work for kind of a system per language will solve the problem of multilingual NLP. Because for every language, there are hundreds or thousands of language varieties. So when we talk about English, no matter how large the data is, our current models primarily work for this variety of New York Times, white male English, right? Formal English. But there are many, many Englishes. Many of them are spoken by millions of people. So only English has millions of speakers across the globe. And the English of an Indian speaker is very, very different from the English of non-native English speaker with a native Russian language. And we can go on and on how different those varieties is and how different our approaches should accommodate to those language varieties. And this is only for individual languages, but the truth is that most of the world is actually multilingual, and multilingual is a gradual phenomenon. So it ranges from language learners like me to fluent speakers. And for bilingual speakers, whenever they use a language with people who use the same set of languages, code switching arises. So in this case, we need to talk about the cross product between language varieties of all set of native languages. And then when we start talking about also domains, right, that language, even dialectal variation in news is different from the same dialect that emerges on Twitter. And these are even more fine-grained, even more dynamic and changing rapidly over time language varieties. So in news, in social media, and also in specialized domains such as doctor's notes or scientific articles or other expert notes, there are emerging dynamic changes that kind of require adaptive models which we currently don't have. And the final bit of motivation is on those domains which are especially kind of prone to adversarial attacks. So these are particularly difficult domains. If you think about the toxic language, first of all, we usually speak about toxic language as hate speech, but there is actually a wide range of toxicity, and many of those can be seen as adversarial attacks on hate speech recognizers. If I say condescending or biased sentence, it might be recognized as positive by hate speech analyzer because they are not equipped to deal with new types of aggression. And in terms of adversarial attack, it is a very well-known fact that hate speech, kind of people who maliciously use language to offend others, they specifically create code words and all kinds of ways to overcome kind of hate speech classifiers. In this case, the techniques also should be always adaptive to the new phenomena that arise in language. And the same is about these examples that already become a cautionary tale, examples of models that discriminate users, that become racist, homophobic. All this is a fact that kind of there are low resource domains within even high resource data that models do not adapt to them. So to summarize this very broad set of examples, they might be unrelated on the surface, but what relates them is no matter how large and carefully curated our data is, we always have low resource scenarios within those kind of always changing domains because the language is so adaptive. So because the language is constantly changing, we need to extract insights about new streams of data. And we don't always have knowledge about the task, about the changes that happen, we don't always have access to human annotators. And also, the changes sometimes are kind of the adversarial examples are sometimes too subtle, even for human annotators to decide whether a sentence is biased, for example. So what I want to advocate for in this talk is, first of all, model-based approaches to extract insights about this kind of emerging, changing domains. So new approaches to interpretability, to work on interpretability, on fundamental techniques, to also apply them more broadly in low-resource NLP scenarios, to uncover model biases, missing annotations, data artifacts through model interpretation. So this is the focus of my talk, to interpretation, to be able to identify the mode latent spurious artifacts in text classification. And this part is kind of not novel. It's obvious we need to work on the interpretability to extract insights about the data. But the kind of novel part that I want to advocate for, and I hope to kind of convince you to do more research in this area, is that until now, research on interpretability has been done primarily for model evaluation, to extract insights about the data. But what else can we do is to use interpretable models in a feedback loop back to the model to automatically improve model generalizations, to demote spurious biases, to make models adaptive to new streams of data. So when we work more on approaches to interpretability, then can be used in a loop in an NLP pipeline with or without human annotators. And this is the focus of my talk. So I will present 2 case studies. In each of those case studies, first I present a novel approach to interpretability, and then I present its application to this kind of low resource, one of those low resource scenarios that I talked about. With the purpose to use interpretability models in a feedback loop back to the model to improve the model. So the first case study is focusing on interpretability via instance attribution. And this covers 2 papers. One is a general technique, and the second is application, like I mentioned, application to improve downstream task using an interpretable model. And the second approach will focus on another new approach to interpretability by design, when we build in interpretable layers into a system, and then another application of it to unsupervised or low resource information extraction. And again, the unifying theme here is that we want to work on interpretability. This is kind of important not only for low resource NLP, but then we want to use model-based interpretations in a feedback loop back to the model in scenarios with scarce resources. This is what is relevant to this workshop. So I start with the first case study, and as I mentioned, the approach to interpretability will be interpretability via instance attribution, and the application that we will focus on will be latent toxicity, veil toxicity, to improve the robustness of hate speech detectors. And there are 3 components here that I'm talking about. First is what is our approach to interpretability. Second is about what is our task. And third is how it's applied in low resource scenario. So let's look at toxicity classifiers. For example, off-the-shelf classifiers such as Perspective API, but it can be any other kind of toxicity classifier off-the-shelf or trained by us. And they usually work as follows. If the sentence is explicitly non-toxic, they will produce a positive label. If the sentence is explicitly or extremely toxic, specifically has kind of words, for lexicons that correspond to predefined lexicons of toxicity, they would produce a negative label. And then there is a large range of possible adversarial scenarios, such as microaggressions, condescension. So a sentence, "You are too pretty to be gay," will likely be labeled as positive by a toxicity classifier, although it is clearly a microaggression. In this case, kind of applications that promote positivity might even promote this kind of microaggressions further. So these kind of microaggressions, condescension, objectification, and bias, existing hate speech recognizers cannot handle them. So, also, it is very difficult to enumerate a priori what are all possible types of such attacks on hate speech classifiers. So we need some automatic kind of system to identify some novel patterns, or to use a couple of examples of a novel pattern to bootstrap them and to make the models more robust. So this is a goal. And this is just references for all kinds of adversarial attacks. This is not a comprehensive list, but it includes adversarial attacks such as code words, so explicit, malicious usages, to kind of unintentional implicit bias, and to other types of phenomena in human communication. And the key observation here is that toxicity classifiers fail on such veiled attacks because their training data does not include relevant examples. So there are two scenarios here. One is specific phenomena such as condescension, for example. They are mislabeled in the training data, so marked as positive, just because kind of those classifiers usually use very rough kind of approximations of the actual training data. It can be annotated by mechanical Turk annotations, who can also kind of miss this phenomena or be biased, or just sampled, for example, to include only kind of sampled using predefined lexicons. So first, these examples may be mislabeled, and second, they may just missing in the set of positive examples. So overall, these are kind of artifacts in the training data that we would try to mitigate or to enhance the training data. And so what we do first is propose a new approach to interpretability. So the popular approach to interpretability, at least until this work that I'm presenting in 2020, is interpretability via salience maps. So this contains a range of possible methods: gradient-based attribution, attention-based interpretability, LIME, Shapley-based interpretability, and hash maps, and other ways to interpret input tokens. But all these fall under the category of interpretability via feature attribution, meaning we have an input sentence, and this approach to interpretability will highlight salience tokens in the input as important for the prediction. But in this case, like I shown the slide, interpretability for microaggressions, this sentence, none of the tokens, the toxicity is not in the lexicon. Toxicity is not in the word, it's more in pragmatics. So none of these interpretability approaches actually would work to surface this toxicity. So what we do, we propose a new approach to interpretability, and the crux of this method is that instead of looking at feature attribution, looking at salient tokens in the input, we want to look at the training data. So we start with model parameters and then track model parameters back to the training data. So this approach to interpretability through instance attribution is not new. It was presented in, say, machine learning conferences in 2017, influence functions by Pankwe Koch. But until this work, it was never kind of applied to NLP because of challenges with computational efficiency. So this is the focus of this paper from ACL 2020. Again, the model makes a prediction, and then we track the model back to model parameters, and then back to training data. And then training data is sorted by its influence. And for example, the most influential, the top ranked influential examples can serve as interpretations to why the model made specific decisions. And there are various ways. This is like a conceptual definition of instance attribution, but there are many plausible ways to operationalize it. One of them can be, so given the kind of the function of influence with a training set and some probing set, there are many plausible ways to operationalize instance attribution. One of them can be as simple as instance attribution via cosine similarity, representation of an example by the model, and representation of all training examples, and cosine similarity to look for most similar examples. Another one is influence functions that I just mentioned. This was presented in ICML 2017, and although I present formulas there, I will just give a general intuition. So intuition is that we want to simulate leave one out prediction, meaning that if we remove an instance from the training data, how much this removal will harm the prediction on the current example. But actually implementing leave one out on kind of language models with hundreds of millions of instances is not feasible. So what influence functions do, they kind of upweight, they look how to upweight individual instances and see how the loss changes based on these perturbations of the training data. These are still very, very inefficient and slow. So in 2020, there was kind of an attempt to approximate influence functions, which propose a method which is not faithful as influence functions are, but much, much more fast. It's called gradient product or trace in, which intuitively kind of it looks at what steps the model makes. If the model makes a step towards the representation, towards the update of the individual examples, and when we aggregate kind of model changes on an individual examples, if these changes are bigger, this means that kind of for the subsets of data for which the changes are bigger, they are more influential on the data. So you can see more details on it, and probably there are other ways to kind of look at instance attribution. So what we did in this work, we experimented with all of those approaches to instance attribution, and we showed how they can be useful for interpreting kind of model decisions when the signal is not in the input sentence. For example, for natural language inference, when the signal, when interpretation is in the reasoning, in the relationship between sentences, but not in individual words. And we show now how to apply it to a low resource scenario of veiled toxicity to make the classifiers more robust. So now I move to the second part of the kind of this case study. One is how to kind of update the model based on this approach to interpretability. So we start with a hate speech classifier. This classifier can be a perspective API when we don't have access to the model, or any other model which we do have access to. In case we don't have kind of the access to the model, we can collect all the data that we think is useful as a training data, all the data that we would like to annotate as a kind of the new stream of data that I was talking about. And we start with training, with creating the training data for the new classifier. We take all this unannotated data and use this off-the-shelf hate speech classifier to tag all the instances as hateful or not. And so we train the, wrong direction. So we train a student model. This student model will perpetuate all biases from the original model. But in practice, it works very well. It can replicate the original model very well. So once we have this student model and the training data annotated by the original classifier, we can go ahead and try to interpret the decisions of this classifier using a small set of probing examples. So these probing examples can correspond to the new phenomena that we want to identify in the input data. For example, these probing examples can be examples of latent toxicity or adversarial examples with new code words and so on. And in practice, we need just a few dozen of such probing examples for the model to work well. In this case, we use about 100. So once we have a set of these probing examples, what we will do, we will use this approach to interpretability through instance attribution. For every example, for every probing example, we will try to interpret classification decision by surfacing the most influential instances in the data. Once we surface these instances in the data, we can examine them. We can either send them to users to reannotate, or we can actually just flip the labels, because when, for those kind of examples on which the model makes the wrong prediction, the most influential instances in the training data might be those that are mislabeled or unannotated in the original training set. So we take the most influential training examples and reannotate them in some way, or sending to users, or just flipping the label. And then we retrain the classifier to make it more robust to this new phenomenon. So this is a general idea. And in terms of evaluation, we experimented with a little bit synthetic setup in which we knew, basically, we had gold annotations on what instances are mislabeled in our training data. So we had 20% of our data was mislabeled or labeled as non-toxic, when in practice it had latent toxicity. And there are more details that kind of in the paper how these samples were selected. They were indeed kind of either instances of microaggressions or some cultural biases, something that kind of more veiled subtle toxicity. So first of all, we can, and then we go through this process. We have a small set, about 100 of probing examples. We train a student classifier. We run the probing examples on this classifier and always select the most influential sets of examples. Once we have the sets of examples that are kind of candidate for reannotation, sets of examples that are problematic in our data, we reannotate and we train the model again. And we evaluate kind of these sets of labels, overt toxicity, positive sentences, and veiled toxicity, mislabeled toxicity in this setup. So before the actual evaluation, I show here the visualization that kind of when we use interpretability approaches on the probing examples. So blue shows actually the examples of veiled toxicity. We see indeed that for specific phenomena, specific veiled toxicity examples, our approach to interpretability surfaces them as more influential in the training data. So these are examples that are likely good candidates for reannotation. And in terms of evaluation, we have many experiments, thorough evaluation. I present only one small subset of experiments. So in the original classifier, it works as expected. It replicates perspective API. It has 99% kind of accuracy on overtly non-toxic examples, about 97% on explicit hate speech, and only 1% accuracy on veiled examples. But when we go through this process of identifying through interpretability candidates for reannotation, then either reannotate them or just flip the label and rerun this evaluation. So if we reannotate properly, the accuracy on the veiled toxicity grows from 1% to 37%. So it's a huge kind of increase, despite the fact that it's still very low and more work needs to be done to kind of deal with this phenomena. And if we even take a very naive approach of just flipping, we can say we prioritize kind of safety. So we want to better fall on kind of false positives than false negatives. Also, there are issues with this approach too. But if we flip all examples, we increase significantly the accuracy on specifically whale toxicity, but we lose the accuracy on clean, non-toxic examples. So there is a lot more work to do. What I present here is a prototype, and taking a point here is that when we work on interpretability, it's important also for downstream applications where we have new type of phenomena that we can tackle using the core interpretability techniques plus the model incorporation. So this concludes the first part of the case study. Still 10 minutes. So case study 2 is yet another approach on interpretability and another application. And in this case, we want to look at built-in interpretability, so how to build actually additional layers to the network to be able to interpret input examples by design. In terms of NLP task, I will be talking about entity or important key phrase detection, so unsupervised information extraction. And the low resource scenario that I will be talking about is, for example, important entity extraction from scientific domain, when we know that the new papers also always appear, and papers about COVID, probably prior models about COVID could not deal with current kind of articles, with new articles. Okay, so again, with the same structure, I start with a general approach to interpretability. This is our AIM-NLP paper from last year, and then its application to the domain of scientific key phrase extraction. So until now, the approaches to interpretability that I presented are basically can be called post hoc. So first we train a model, and then we try interpret this model through feature attribution or through instance attribution or through training data. Both approaches are useful in various conditions, but what we want to do, we want to be able to build more interpretable models that are interpretable by design, and also combine post hoc interpretation and instance attribution within a single model. And the second kind of goal of this project was to kind of point out that even if we want to do feature attribution, we don't want to attribute kind of the importance to subwords. It doesn't make sense. What we want to do is to attribute the importance to concepts, and the concepts can be relevant to the task. So in the case of key phrase extraction, these concepts can be noun phrases. In the case of event detection, these concepts can be verb phrases and so on. So we want kind of to have linguistically meaningful units for interpretation and have built-in interpretability within the model. So this is a paper that is called Self-Explain from AIM-NLP last year. And basically what we do is what I just described as a motivation. This is an architecture of Self-Explain. I realized that the drawing is not very self-explainable, so I will go over various parts of it and to explain what we do. Overall, we have kind of a pre-processing stage when we do concept extraction. This concept should be relevant for the task. Then we do represent every concept as an embedding in addition to individual tokens. And then we add two layers. So the layer on the left is a local interpretability layer that basically does interpretability through feature attribution. And the layer on the right is global interpretability layer, which does interpretability through instance attribution, through important instances in the training data. So in terms of concept-aware encoder, the preprocessing, we use just, in this work, we use constituency trees. We extract all well-formed verb constituents, linguistic phrases, and we do, let me just get rid of the animation. And we do, for every token and then for every concept, we represent the embeddings by mean pooling of all constituting tokens. So these are embeddings of our concepts. Then we have a local interpretability layer, and this local interpretability layer, it basically simulates, sorry. Yeah. It simulates the leave one out approach. So what we do, we take the embedding of the root of the sentence, and then we remove an embedding of the concept, and we see how much the loss changes as a result of removal of individual phrases from the prediction. So it's a kind of simulation of leave one out on the prediction of the original label for which the classifier is trained. And the global interpretability layer is a realm style layer which does information extraction. So we have a concept store, a set of phrases, and at every kind of iteration or every few epochs, we extract, for every input example, we extract influential phrases from the training data and update the concept store. We extract it using a minimum product search. And basically, as the model is fine-tuned on downstream task, the representations in the concept store are being updated constantly. And kind of they're being updated every few fixed number of steps. So now we have the global interpretability layer, the local interpretability layer, and we train the whole system, all three layers, using the downstream task. It can be kind of any classification task, hate speech detection, sentiment analysis, and we use regularization to make the all layers kind of outputs agree between themselves. And because Jean is showing that I have only 4 minutes left, I'm skipping on all the evaluation. I can just say that both in automatic evaluation and manual evaluation, those interpretations are shown to be better than interpretations, post hoc interpretations. We compare it both to saliency map and to instance attribution, and they're shown to be better. And also we don't lose on the accuracy of downstream task. So, and then the second part, the application of it to unsupervised information extraction would be on scientific domains. So we take the papers, and what we want to do is extract important key phrases in the papers without any supervision. So we use self-explain in the following setup. We have scientific article. We first extract topics from the scientific article using your favorite unsupervised topic modeling approach. Then we train self-explain the model with the local and global interpretability layer in a multi-class classification setup to predict the topics. And then we use local interpretability layer to identify important influential concepts that are considered as key phrases. And again, skipping on evaluation, I hope you can read the papers. Kind of this approach actually outperforms existing approaches, graph-based approaches, neural approaches to key phrase extraction. Okay, so to summarize, I presented 2 case studies. In each case study, there is a general approach to interpretability, and then its application to low resource scenario. There are many other ideas how interpretability can be used in low resource setting. So one idea is that we are currently finalizing a paper on is demoting bias, racial bias, and hate speech detection by detecting influential phrases in self-explain that make the decision. So what we want to do, we want to promote, for example, toxicity lexicons and demote the signals of, say, African-American dialect. And any other ideas that we are working on, which I'm skipping on, and the general idea that kind of I want you to think about if you like this direction is let's work fundamentally on interpretation and then use these interpretations as a feedback loop to improve downstream models, thereby improving both low resource NLP and just general approaches to interpretability. And the final slide is, nobody asked me, but since I'm local, if you have a chance to go to Green Lake, if you like the nature, I think you will enjoy it. And thank you. Sorry for running a little bit over time.
Thank you, Yulia. We have time for a couple of questions. Please go ahead to the mic.
Oh, thank you for the talk. I was wondering, like the first part, you were saying that there are some like emergent types of microaggressions or something that we are not aware of. I was wondering, like, if using some kind of user signal would be like the better approach. Like, if you, of course, if you get access, like to, let's say, people on the social media platform, like groups of people, like cliques of people using specific lexicon that you don't understand.
Yeah, that's a great question. And the answer is, specifically, we want to look at interpretability and unsupervised approaches because there are no good lexicons for it. This is like core pragmatic task, like examples that I showed, like you are too smart for a girl. All words can be positive. And also when you just take these microaggressions and send them to human annotators, it doesn't matter if they're mechanical Turk annotators or researchers like you and I, annotators will always incorporate their all biases, their personal biases, right? So it's a really difficult task to use either lexicons or manual annotations. And that's why we need to think about unsupervised approaches or some workarounds to leverage bias, to defeat bias. Thank you.
Hey, John Clark from Google Seattle. Thanks for the really nice talk, by the way.
Thank you.
I definitely see the parallels with what you're talking about here with multilinguality, and I'm curious if you have any thoughts about how can we use something like self-explain to figure out where benefits are coming from in our current scenario. So people come and say, oh, this is like magic that this works across all the languages in zero shot, but can you help us explain?
I love this question. This is exactly what I was trying to convince my student to work on. I don't know about self-explain, honestly. I like the idea of using self-explain, but I like more the idea of using the first part of interpretability via instance attribution. And basically, when we train polyglot models or multilingual models, we don't always know how they share, whether they share parameters actually in a meaningful way. So what we can do is a future work, instance attribution. This instance attribution actually is determined by activations in the model itself. So as a follow-up research, I would want to see visualization of those activations and understanding what model parameters are activized when the model attends to influential training examples. So it's both interpretability and kind of interpretability of the model, not only like the input data. And I think this is an interesting direction for looking at multilinguality, and then various ways to bias those parameters, to regularize the models, to make them actually share parameters when it's meaningful to share parameters, or kind of to distill models to get rid of spurious artifacts that will improve the performance on multilingual tasks. So I think it's a very interesting future direction of research. I haven't seen anything like this yet. Thank you.
Do you have more questions? I do have one more question if no one else does. So the other thing we have in modern multilingual setups is both this pre-training phase and a fine-tuning phase.
Yes.
Do you think there's anything that these tools have to offer to help us know, is this coming from the pre-training data versus the fine-tuning data as well?
This is a good question. So we currently have a paper, sorry for the plug, but I'm not mentioning the paper, it's in submission, that actually look at kind of trying to interpret much bigger models used with prompt tuning, specifically looking at pre-training data. And it is much, much harder. Maybe for you folks in Google, it will be less a problem. For us, it was very, very difficult. For Han, my PhD student, it was very, very difficult to make it work. But kind of, I like the idea of looking at pre-training data, with prompt tuning, without fine tuning, basically understanding the influence of training data, and then with fine tuning, understanding the influence of fine tuning data, and doing analysis through this. Yeah. Thank you for the questions.
I do have a question for Yulia.
Yeah.
So I'm particularly interested in the evaluation aspect of all the problems you talked about today. So like for both kind of like instant level and feature level attribution kind of approaches, what do you see are the important aspects for like evaluating the progress you make on the problem? Because we know like people, I mean, community be doing like in-domain or IID evaluations for a while.
Yeah.
We know it's not going to work for
Yeah,
all these
that's
like shortcut learning problems.
important question. I know also your students just had a very nice paper on evaluation. I totally agree that evaluation of interpretability is as challenging as interpretability of neural networks. So in self-explain and in enhanced paper, we did a bunch of experiments by using automatic evaluation, for example, sufficiency, when you use kind of only interpretations to perform the task rather than the whole input and see if it's sufficient. So it's an example of automatic evaluation. And there is a bunch of possible manual evaluations in prior research on reliability, on trustworthiness of explanations, which are done basically by human annotators. So yeah, that's a good question. There is a lot of attempts to do evaluation. None of them is great. I think the hardest one is to understand the faithfulness of interpretations. Everybody is talking about it, specifically for self-explain. We cannot prove mathematically that the model is faithful. We were just fine-tuning it kind of to be faithful by design, but we don't know if it's faithful. And how to evaluate it, it's very difficult. So I cannot answer this question in a perfect way because I think community doesn't know how to evaluate the systems well.
Yeah, I agree. I think it's an important question. Great. Let's thank Yulia again for the
Thank you very much.
Awesome. So we'll be moving on to the next part, which is the second poster sections of the workshop. And this will be a hybrid poster sections. If you're interested in seeing those in-person presenters, you will be seeing them at the 7th floor, the demo room. There will be posters there, and there will be the another majority of the presenters will be on GatherTown, which you will find a link on the underline, just like the first poster section. And then after that, which I think it's in an hour, so we'll be back around 3:15 to the room, and we'll have the next invited speaker, and to continue with the workshop. So please feel free to attend the kind of the versions that you like to. Thank you.
We met, we met very briefly when I was a visiting admin at student, but now we're here. Sean, do you need any help for me, like volunteer-wise, during the poster session? Okay, then I'll be back in the seat. I heard you on the panel in there, floating between rooms, and It's really, really interesting. Yeah. Yeah. Good to see you.
No, there's nothing here. I think I told you there is also one computer here for you to control. No, Unity control is also with that.
Hello. Hello. Actually, it might be nice if we could. Is this table easy to move to the other side?
Yes.
No. I just want this, like, if it's over here. Oops.
That's not so easy.
Yeah.
There are some. Just move it from the base.
Yeah, I think we should get the top back in first. Could you put it down for a second? Then we'll rotate. Back. The top's not on the base. But let's get the top. Yeah. Oh, so wait. There. Over here. And I can say that like right here. Okay.
Right.
Yes.
Hello, everyone. Welcome back to the last session of DeepLo for this year. And I, Sharon Khadibi, from one of the co-organizer of this workshop and research scientist at eBay. I would like to introduce our next invited speakers, Graham Neubig. Graham is associate professor at the Language Technology Institute of CMU. His research focuses on multilingual natural language processing, natural language interfaces to computers, and machine learning methods for NLP. Today, topic for the title is can we automatically create language learning textbooks? Thanks for coming.
Yeah, so thank you for having me, and I'm happy to be able to present our work about this. This is work mainly by Aditi Chowdhury, who just graduated from the PhD program, along with many collaborators at CMU and elsewhere who I've listed here. So yes, let's get started. Oh, and I should point out, we have a website that you can take a look at here to see some of the extracted rules and stuff that I'm going to be talking about. So if you'd like to take a look, please go ahead. Okay. So as we know, there are many languages in the world and remarkable language diversity among the languages. And so for example, in English, we might have a sentence that looks a bit like this, or Marathi, which is Aditi's native language, might look a little bit like this. And they have different linguistic traits, such as Marathi being an SOV language, or English being an SVO language with the verb in the middle. And, this is just the most obvious trait that, everybody knows about, but of course, there's lots of little variations between languages as well. And so if we look at the different systems governing language, syntax, which I just talked about, is obviously one of them. But there's also other things like morphology. So, from English, we have eat turning into eating. And then in Marathi, we have something analogous, except we have different conjugations for whether it's a masculine or feminine subject. We also have semantics. And so this is just one example here. In English, we would probably call both of these rice, or we would have to use another word to distinguish between them. But in Marathi and also other languages where rice is a very prevalent staple food, you might have different words for each of these two concepts. So there's a different word, tandul, for raw rice, and bhat for cooked rice. So this is a kind of lexical distinction that we don't necessarily have in English, but you would need to know in order to know this language fluently. So describing systems of language is the goal of this talk, and there's a lot of reasons why we might want to be able to do this. So for example, language learning. And I like this example from Wikibooks for Spanish because it's a very organic example of language learning materials that were created, and also you can go and take a look at them online without buying a book or anything. But it just has many examples of things like the gender of Spanish nouns is usually pretty easy to work out. Some very simple rules of thumb. If a noun ends in A, it's likely to be feminine. Example, bolsa. If it ends in O or a consonant, it's likely to be masculine. Examples, libro, mobile. There are exceptions though, but you will learn these as you attain new vocabulary. So this is like a very good motivating example for what we're trying to do here. We're trying to describe the rules of language, but we're also trying to describe the exceptions and the other things like this. So that's kind of the theme of this talk here. Just have one more example. When we want to turn a noun into the plural, we follow these rules. If the noun ends in a vowel, add S. If the noun ends in a consonant, add ES. So this is another kind of like if-else statement that has to do with how we do conjugation. This also can be useful for things like language documentation, which instead of being focused at language learners is focused at linguists who would like to learn more about the language. And one of the large things that linguists who are encountering a new language do is they either look up a grammar, like we just have a few examples here that talk about things like phonology, morphology, syntax, etc. Or maybe they have to go and create a grammar from scratch if one doesn't exist for the language or language variety they're working in. So to look a little bit deeper, we might have a language description that says, how are the subjects ordered with regard to verbs in Marathi? And the answer here, we can look at nouns and we can look at syntactic structure like dependency structure. And then we can say, well, we see that the subject comes first, the object comes second, and then we have a verb. So this is likely SOV order. So why is this challenging? I would argue that one of the main reasons why this is challenging is because we have a lot of languages for which we would like to do this. You know, there's approximately 7,000 languages in the world, depending on how you count. And it's non-trivial to do this because, you know, in order to account for all of the languages, we would need to have good syntactic analyzers. We'd have to have good ways to describe the results that we get from these syntactic analyzers to people who would need them to be, for example, learning a language or documenting a language. And so the question is, could we help in this process in some way? So one thing to note is that NLP, rather standard NLP tasks already do some portion of this to some degree of accuracy. So, you know, the top part obviously is dependency parsing. The bottom part is POS tagging. And, you know, some people might tell you if they're building end-to-end NLP systems for QA that they're not using dependency parsing or POS tagging for these systems because they just trained them end-to-end. But I am super excited about dependency parsing and part of speech tagging. And this talk is the reason why. I think you can use them in human-facing applications to do really interesting things. So basically, our proposed pipeline is based on Aditi's thesis work, and it consists of a whole bunch of different papers that we've published at different points from 2020 to now. And the first thing is low resource language analysis. This is something, you know, everybody here has been talking about for the entire day. And then it's also based on something we call the AutoLex language explorer, which is, you know, the link that I also showed at the beginning of my presentation. And in addition to this, very recently, we have started to apply the extracted language descriptions from the system to applications. And one of the big ones that I care about is language education and documentation. So AutoLex stands for Automatic Language Explorer. And the idea is we'd like to extract and visualize answers to different linguistic questions in both human and machine readable formats. And some examples would be like the one I talked before, how are subjects ordered in Marathi? And what we do is we take a text corpus and then, you know, we have this big gear that we turn through AutoLex, and it gives us something that looks like this. It says, generally, the word order for subject verb is before. In other words, the subject comes before the verb. Some examples are, you can click on the examples and it shows you examples of this. But the subject is after the verb when the verb is also governing a word or the subject is near a compound. The subject is governed by a word with an aspect simp. So basically, this is telling you most of the time, it takes this particular grammatical structure, but some of the time it takes something else, and we're going to show you examples of that too. So I had this one gear of AutoLex, but of course the process is more complicated than this. And basically it's a 4-step process. The first step is that we formulate the linguistic question into a classification task. The second step is we extract features and construct training data. Then we learn an interpretable model to solve this task, and we take the interpretable model and we extract and visualize rules. So there are 2 ways to extract features and construct training data for this. The first way is if we already have expert annotations for a large amount of data, such as through a tree bank, we can directly use the annotations that we already have and kind of extract high-level insights about the language structure. Or alternatively, if we don't have those annotations already, we can train a low-resource dependency parser, or part of speech tagger, and use that to annotate a whole bunch of data that we have in the language, and use that to extract the rules and present examples to people. And so for many languages where we have good annotated tree banks, of course, this would the former method would be more appropriate. But for languages where we don't have very much data, the latter method would be necessary. And we might even have no data in the language, in which case we'd have to do zero-shot transfer from another language and hopefully still get part of speech tags or dependency parsers that are good enough to use. So what are the types of grammar or language that we can describe in AutoLex? So we tried several different things. The first one is morphological agreement, word order, affix usage, case marking, and word usage. And these are motivated by basically our study of the types of things that people learn in language learning textbooks. I'm going to talk about this a bit more in the latter part of the talk. But basically, we have these 5 things. And the first ones are kind of what we typically call morphosyntax. And the final one is what we call lexical semantics. So basically, what I want to demonstrate is this methodology is useful for kind of a wide variety of like linguistic questions we might ask about a language. So once we have our linguistic questions we want to ask, we formulate them into a classification task and go through the whole pipeline. And I'd like to start out with an example of word order, because I feel like word order is kind of the easy to understand version of this. So word order. I think a lot of people here are familiar with the word atlas of language structures. And the world atlas of language structures, basically what it does is it has a variety of features like order of subject, object, and verb, order of adposition in noun phrase, order of genitive and noun, et cetera, et cetera, et cetera. And it has these for a very large number of languages. So this is a great resource. It's really wonderful that number one, linguists have started documenting this information, and number two, that it was organized into a format such as WALS. Here's an example of object-verb order, which also is highly correlated with whether it's SOV or SVO language. But there's a problem here, which is that it's either listing a single order for the language, or it's listing no dominant order for the language. And no matter which language it is, it's rarely this simplistic of a distinction between the orderings. So, almost every language has exceptions to this rule, and that is definitely not specified in WALS. So just to give an example from English, which presumably, everybody here kind of knows to some level intuitively, if we look at the object and verb in these English sentences, in this first sentence, it's the typical verb-object order, but in this sentence here, it's actually object-verb. So English is not uniformly SVO. It's not uniformly the object coming after the verb. And so then if we formulate a linguistic question as when do objects come before or after verbs, ideally, we would be able to discover an interesting rule about English that we could then teach to English learners or any other language in the world. So what we do is we take inputs, and so in this case we take like eating an apple and a whole bunch of features that we could extract from eating an apple, and we get a classifier to predict the label before. And then we also have what in eating and all the features that we can extract from what in eating, and we have it predict the label after. And so then we take these examples, and when I said feature extraction, what we want to do is we want to extract features that are also easy to explain to humans. So for example, what is the part of speech of the words? What is the relationship between them? What are the morphological features of the words? And then we take these things like is object noun, is object pronoun, is verb tense present, is object interrogative, is verb tense present. And then we take these features, we take these labels, and we learn a model. And specifically, we want to learn a model that we can then explain to learners who also want to form their own mental model of how the language works. And so we can't just throw it into, a neural network and show our learners like weights from the neural network. And so what we do instead is we take, the typical interpretable machine learning method, decision trees. And so we form a decision tree. And then if the decision tree looks like this, we start out at the root. And if the object is a pronoun and the object is interrogative, we say that the answer is that the object comes before the verb, and otherwise the object comes after the verb. And so basically this is the exact thing that I showed before in our kind of like language browser. Sorry, my Zoom is getting in the way of my slides. Okay, so we'd like to compare the model in a clean setting. And because of this, we use the syntactic universal dependencies corpora. This is a version of the universal dependencies corpus. I'm not sure if everybody's familiar with this, or some people are familiar with this, but basically universal dependencies are semantic dependencies. And so they make certain assumptions based on the dependencies, for example, auxiliary verbs are the child of the main verb, whereas in like syntactic dependencies, usually auxiliaries would be the head. And so this syntactic universal dependencies prefers syntactic heads over content heads, and it's more conducive to our goal of describing the grammar of the language. We have expert annotated syntactic analyses for more than 60 languages, and it's growing, constantly. And so basically, what we do is we train a model using the features extracted from these clean dependency parsers and apply it on held out sentences. And what we can see is that the model learns to predict whether things come before or after on held out data better than a baseline of saying, like in English, the object always comes after the verb. So, if our model is able to successfully describe, our model is able to successfully predict this, then it's probably also a good description of the actual rules of the language. And I don't have many details about this in our talk, but we can also do things like limit our models to a certain depth, or limit our models to a certain number of nodes. And by doing so, we can control the complexity. So the rules that we display to learners are either more simple or more detailed. So this is an example of Spanish adjective noun ordering. In Spanish, adjective noun ordering is a bit more complex than English, verb object ordering, in that if you take the majority baseline and say the Spanish adjective always comes after the noun, then you're going to be wrong about 32% of the time, because in Spanish it is actually quite common to also put the adjective before the noun. And so even if we use the syntactic signals here, even if we talk about the part of speech and other things like this, this is insufficient to bump the accuracy much higher than like 73%. So what is missing here? If we look at Spanish, we can see that actually, for example, a adjective like grandes tends to come before the noun libros, and adjective like pequeña tends to come after the noun. And so, like, even within this simple sentence here, we see two examples. And so we take the syntactic rules, and they're basically like more or less the same, other than this one being ordinal and this one not being ordinal. And so what we also did was we extracted lexical features. So like we have like the lemma, and so then we can explicitly memorize words that tend to follow uncommon patterns. And actually, if you look at Spanish learning materials, they have these explicit lists of words that say most adjectives come after nouns except these ones. So this is another thing we can display to learners. And if we look at the result, this bumps our accuracy up by quite a bit. So, you know, we've done a better job of describing the language. And we can get leafs that look a little bit like this. So it says typically, so if it's adjective and ordinal, it comes before. If it's an adjective and it's grande, or if it's an adjective and it's nuevo, these come before. So it's basically like learned a list of the words for which there are exceptions. So in addition, we might want to generalize even farther than this. And so we further went into word embeddings that capture semantic and syntactic similarity between the words. So this could say something like, well, normally nouns, normally you have this syntactic structure, except when the noun is animate, something changes. So, you know, all animate nouns might be clustered in word embedding space. So this would allow you to say something about semantics as well. However, we tried using original word embeddings, and it's actually quite hard to extract interpretable features from them. So what we did was we specifically used sparse word embeddings, and sparse word embeddings are essentially more interpretable because they make each dimension of the word embedding more meaningful. And so we use this method called spine that does post hoc sparsification of word embeddings. And we can see that after we do this, we look at each dimension. Each dimension is kind of meaningful, like wrist, shoulder, ligament, ankle, thigh, extensively, adequately, traditionally, royally, fully, other things like this. There's also, you know, like each word can appear in different embeddings, of course, but yeah, there's that as well. So from the semantic embeddings, we can then extract things like the word is like other words, or things like this. And so this allows us to generalize even beyond what we would normally be able to do if we just had lexical embeddings or lexical features. And we can see that this also improves our accuracy. So basically what we've done here is now we have our decision tree, and we extract and visualize rules to show to the language learners. And so we could extract every single rule from a decision tree, but actually some of the rules kind of are there by chance, or they aren't really very meaningful. So like, for example, if after is 1000 and before is 1800, it really might not be saying very much about, you know, whether this rule is a meaningful rule. So in addition, we also added some statistical tests to tell whether this rule is like something actually meaningful or it's something that is, you know, just due to chance and how the data is working out. So if it is judged as meaningful, then we add it to our list of rules that we display to people. And like, as I mentioned before, this is what the rules look like. We talk about the dominant order in the corpus, and then we have all of these exceptions and examples that we can present to people. So we also have the examples that we show to people who are who can browse them. So we have like Primera Vez and Plata Primera. So like it's not the case that Primera always comes before this, and that can also give people intuition about how the language works. So we did this for a bunch of other tasks. I'm just going to kind of like blaze through them to not bore you with the details, but basically we looked at agreement. So we look at whether there's morphological agreement between, for example, the noun and the verb, which is a very big thing in you know, many languages with rich morphology. So in this case, it agrees. This case, it doesn't agree because it's a masculine noun and feminine noun and a masculine verb. And so what we do is we essentially we ask a similar question of when should a head dependent agree on gender and when it shouldn't, head dependent pair. And so once we've extracted all of these rules for all of these different categories, we did a quality evaluation by asking human annotators to tell us whether they were good or not. And if we look at this, we say looking at the examples below, is the rule precisely defining a linguistic distinction? Like, in other words, is it correct? Is it something that you knew already? And do the features actually accurately describe the group of positive examples? So is it readable? And we basically found that, in many cases, it's reasonable, it's like precise or too specific or too general, but still a valid rule. And 80% of the rules were found to be valid, 69 informative and readable. And also in some cases, even for well-studied languages, the system would discover things that the annotators didn't necessarily consider a priori. And this is kind of interesting as well, because like even for somebody who doesn't know the language, like let's say it's a linguist who is, let's say it's a linguist who wants to create a grammatical description of the language, they might know the language relatively well, but they might not know all the ins and outs of the language, or they might have not written all of them in their grammatical descriptions. So even for well-studied languages, it discovered things like this. Like this is a rule that I didn't know a priori, or I didn't think about a priori, like anything else being an example of where adjectives come after pronouns in English. So an aside, if you care mostly about model development and not about about the downstream application of language learning, this is a really important issue, which is that parser quality matters a lot. So we tried to apply autolex on Hmong, which is endangered or threatened language, which has no syntactic parser available. So we did a variety of things, like we did zero-shot transfer. We tried to annotate a little bit of data and do few-shot adaptation. And we discovered 30 rules for subject, verb, object, verb, etc. word orders, but only 16% showed valid patterns. And the linguists basically said this is not very useful. We applied autolex on Kannada, which had no syntactic parser, but had related language data and a small amount of annotated data. And we used few-shot transfer with all the available data that we had. And for subject verb and object verb orders, nearly 50% showed valid patterns. So basically what this is saying is, the work that we're doing on low resource syntactic analysis or things like this really does have a big effect on a downstream application like this. So if anybody tells you it's not useful, then they're wrong. So going back and revisiting our research goal, like all of this, there's a lot of technical detail here. It's a pipeline system, maybe not as, impressive as training a big pre-trained model on multilingual BERT or something. But I think if we go back to why we want to do this in the first place, we had our low resource language analysis, our automatic language explorer, and we also had applications of language education and documentation. And this is part of the reason why I'm most excited about this and why I really wanted to present it now to a big audience here, which is that we looked into the possibility of this for actually being useful in language education. And computer-aided language learning systems or computer-facilitated language learning systems are in really high demand. We look at things like Duolingo or Rosetta Stone. These are great. Many people use them, but they're still relatively limited in their language coverage. And part of the reason why is because most of these create curricula based on human annotated grammar rules, or at the very least templates to create examples. And in order to get good grammar coverage examples and exercises, it's hard to handle this. And so autolex, our goal is to either completely automatically or with a human in the loop, make this process easier so we can make language education more accessible, and especially make it more accessible to people who are speaking long tail languages that, for example, have not seen very much resources put into building language learning materials for them. And so the first thing I'd like to talk about from the point of view of language education, where we actually did a study to see whether we could teach people how languages work. We also had another variety of prediction problem that we handled, which is semantics, lexical semantic problem. And specifically, we looked at how different languages carve up the semantic space differently. And this is the kind of like headline example from our paper at EMNLP last year, which is in English, we have the word wall. And then in Spanish, we have different words, muro and pared. And I didn't know this distinction a priori, but basically, muro stands for an outside wall and pared stands for an inside wall. And so what we did was we did a crowdsourced study with a whole bunch of words like this that have one word in English and multiple words in another language. And we crowdsourced a study where we recruited participants, had to predict the correct word usage in context. And here are the results here. And basically what we did was we showed them only examples from the language. And then before we showed them examples, we showed them a small number of rules describing why one word usage was used rather than the other. And basically what we could see was when learners were shown rules, they learned both better, kind of overall, even Greek learners after viewing 120 examples, and they learned much faster. So like before they even started looking at examples, they were already able to predict better what the correct choice would be. And we did this for like 9 different words for Spanish, 10 different words for Greek, with a pretty significant difference. So another thing that we did that actually has had some practical impact already is we applied AutoLex to extract grammar aspects for teaching 2 Indian languages, specifically Marathi, which is from central India in the Indo-Aryan language family, and Kannada, which is from farther south in India from the Dravidian language family. And specifically, we created language learning materials for heritage language speakers who were born and grew up outside of India. Most of them spoke English as their native language. And so this is the very common setting where it's somebody who, their parents or their grandparents spoke the language, but they want to learn their heritage language, but didn't grow up speaking it. And so what we did, and number one, they're under-resourced settings with regards to pedagogical resources. There aren't very many resources. There also aren't very many NLP resources. But what we did was we found teachers who were teaching these languages actively at schools, and we collaborated with them basically to try to make this tool something that would be useful for them in their teaching. And for Kannada, we worked with something called the Kannada Academy. It's a volunteer organization with 70 learning centers and 800 volunteer teachers. They've created learning materials for all of the students, and specifically 2 of our co-authors on the paper that we recently archived about this was Arun Sampath, the director of academics, and Ashwin, who's basically a polyglot and learning, and knows a lot of different languages, including Kannada, his native language. And then for Marathi, we worked with a few schools in Randolph, New Jersey, and Pittsburgh. And these are much smaller, independent, volunteer-run schools. So the way we selected the grammar aspects to use was we consulted with the people who were designing curricula. And we also perused existing textbooks to identify the grammar points that were already being taught in the textbooks to decide the ones that we wanted to be identifying ourselves. And so we went through and did a classification of all of the grammar points and like what kind of categories they were using, and like what the questions were and things like this, and use this to kind of design our approach. And so in doing this, we added one more thing, which was like inflection tables like this. So this wasn't part of our original AutoLex tool, but looking at the teaching materials that they were using, this seemed very important. So we further added this feature. We also added agreement, word order, affix usage, and essentially did a very similar process as well. And we also did word usage, like when you use certain kinship terms and other things like this. And and here's an example. We also, we noticed that for vocabulary learning, the textbooks tended to group together similar terms. I mean, if you learned a second language, this is not surprising, but we hadn't thought about it before. So we also tried to group terms according to their semantic categories. So yeah, maybe I'll skip that part. So then we took these. We would like to have a Kannada parser and a Marathi parser, but no sufficiently good ones existed immediately. Basically they had no UD tree banks and very small and noisy UD tree banks. But there was some data to be found. So what we found was actually there was a separate tree bank not yet incorporated into UD that we were able to convert to basically something very similar to SUD. And this is called the Paninian tree banks. And then on top of this, we used UD zero-shot transfer to train models for part of speech tagging, lemmatization, and morphological analysis. And for dependency parsing, we did transfer from Hindi because that was the largest related language that we had. So based on this, we ran the pipeline that I described up to this point, did the linguistic questions for all of them, and we did quality studies with the teachers who were in service. We did automated evaluation over like nouns and verbs classes and verified that things worked better than chance. And then finally, we did a study with teachers to see what their perception of these were. And they evaluated the relevance, utility, and presentation of the materials with 12 Kannada teachers and 5 Marathi teachers. We introduced it to them. We gave them 1 to 2 weeks to do exploration, and we had them fill in a questionnaire. For relevance, they gave about 50 to 70% of the materials were relevant for Kannada. For Marathi, it was much lower. And part of the reason why was because Marathi was focusing very heavily on beginner learners. And the underlying data that we used was too complicated. It was like legal texts and other things like this. And so because of this, one thing we learned here was that the underlying text that we used was very important. And so getting appropriate text to learn these materials is good. And then we also asked them for what purpose they would be using these materials: lesson preparation, student self-exploration, and student evaluation. We found that they thought they would be most useful in preparing lessons because it's kind of advanced materials that the teachers can understand, but maybe the students could not. And we got a lot of testimonials, like they thought the illustrative examples were good. One of the teachers actually used the examples that we had in their lessons to teach an American student and other things like this. Basically, they thought it would be more useful for older learners, but I think that's actually good in a way, because very often there are like beginner learning materials for many of these languages, but not more advanced learning materials. So we also have applied similar rules to other applications like automatic multilingual grammar checkers and other things like this, but that's kind of beyond the scope of the talk. But if you're interested, you can take a look at the paper. Great. Yeah, so that's basically my talk. I'm also out of time, but The basic idea is AutoLex is a framework to extract and visualize language descriptions where you formulate a linguistic question, extract features, learn an interpretable model, extract and visualize rules. All of this is available here. And we've demonstrated at least a little bit the real world utility of doing things like this. And I think the most exciting thing for me is now that we have a connection of, under-resourced dependency parsing for under-resourced languages, or syntactic analysis for under-resourced languages to something that, really I believe is very useful in the real world. I can now with confidence say, now we really need to improve our dependency parsing accuracy on zero-shot or few-shot settings. This is something where you can really use it for. So that's all I have, and please take a look at the site if you're interested. So yeah, thank you.
Yeah, thank you. Very interesting talk. I was wondering, if there is a way to discover, you said it always starts with formulating a question and then finding support for it in the data, but discovering which questions to ask. So for instance, there are languages that I know very little about, and maybe there are some phenomena that I didn't even think about. Can we leverage crowdsourcing for it, or something semi-automated? Do you have any ideas?
So number one, the crowdsourcing idea is a great idea. If we, it doesn't even need to be crowdsourcing on Mechanical Turk. It can be crowdsourcing to language teachers or linguists or something like that. And I think basically what we would need to do is we would need to have a way to go from maybe either have them specify it in a way that's sufficiently formal that it could be ingested directly by the system, or, have some way to go from a vague description of an interesting linguistic question posed by a linguist or a language learner into the more formal representation that we need for this. But I don't know if there's any way to easily automate it, but I think it's a great question. Yeah, but thank you.
Hello, this is Neha from Johns Hopkins. Great talk. I thought this was a really cool use of part-of-speech tagging and dependency parsing for language learning. I noticed that I think probably due to time you skipped really quick over a transliteration slide, but I was quite curious as a heritage learner of an Indian language myself, how did you use that to help learn script, or if you could say a few words about script and transliteration for whatever is built into AutoLex, that'd be great.
Yeah, that's a really good question, and I myself have used transliteration in trying to understand languages that I was working on, and basically you don't know the script. It's impossible to even tell if two words are the same or they have the same inflection or something like this. I think fortunately for many Indian languages, there are very good out-of-the-box transliterators. I don't actually, Aditi did this work, and I don't actually remember exactly which one she used, but I think that's really important to have. I don't know if I can give much more of a comment than that, but okay. Yeah.
No, thank you.
Yeah.
The question, is alphabet really a problem for a learner? Because I guess the learner just spends the first day of learning the alphabet, and then they it's not a problem. It's more for researchers working with these languages.
Yeah, you're right. I do think that the script should be perhaps the first thing that learners learn.
Unless it's a complicated script.
Yeah, unless it's a complicated script. So yeah, I maybe more for linguists than learners, or for people who are casually browsing things. Yeah.
I guess I was just curious because there's not a huge culture of learning script necessarily, and a lot of people just write things transliterated anyway, so it's sort of how you want to teach it. So that was due to my question.
Yeah, thank you.
Hi, yeah, thanks for your talk, Economy. So maybe one idea and one question. So related to Alex's question about what are the questions to ask. So one thing I think I would find useful is that if you could input the language that you know, and then the system would highlight sort of what are the main grammatical differences compared to some of the known languages. but yeah, so the question I wanted to ask was that it seems that probably this automatic generation of language learning resources would be most useful for very low resource languages, where you also are probably unlikely to have parsers or part-of-speech stackers. So can you maybe elaborate a bit on how much work was it to do this kind of zero-shot training of these Marathi and Kannada stackers and parsers?
Yeah, so there were two things there. I'll actually try to answer both of them. So the first one is if you can contrast to a language that you already know when you're learning, it's way easier. So for example, I speak English and Japanese, and when I tried to learn Korean, it was way easier for me to learn Korean from a Japanese textbook because, you know, the languages are so similar. And I think there's nothing in our methodology here that limits you to describing the language in English, other than, you know, we'd have to maybe have a few templates that we'd have to translate. In order to get some things, you do need aligned parallel data. So like if you wanted to align Hindi to Marathi or Hindi to Kannada, you would need like parallel data for that, but there are parallel data sets to some extent. So that would be the limiting factor there. And then the second question was, sorry, what was the second?
How much work is it to train these part-of-speech?
Yeah, right. So I think it's a good point. This would be most useful in languages that don't have very many resources, but I do think that the pedagogical resources are actually less than the tree bank resources in many cases. Like just, you know, Hindi and Marathi and Kannada are examples of this, where there really are a pretty limited number of advanced language learning textbooks, but there still are, you know, a tree bank, for example. For zero-shot parsing, it depends how similar a language there is with, you know, a high resource tree bank and, you know, how well transfer works. So I think like zero-shot transfer might work quite well into some languages where there's similar, you know, similar annotated tree banks. But we tried once for Hmong, which was probably a less good idea. And then, you know, we did transfer from Hindi to Marathi and Kannada. So it is useful in some cases, but it wasn't useful out of the box in others.
Cool, thanks.
I don't have a question, but just for the previous question about transliteration, like on the iOS keyboard, now there is a feature to transliterate, and that uses a seek-to-seek model. And it's there for English to Marathi and many other Indian languages.
Okay, great, thank you.
I'm Sean from Amazon. Thanks for sharing the great work. Let me see if I can show it up a little. All right, so I'm really curious about the AutoLex part where you generate the rules. I see that right now you're using a classifier to form sort of a hypothesis on what rules are there. But it feels like if we have a high quality parser, it should be possible to also try to mine counterexamples and use that as a verification rather than just relying on human.
Yes, we actually do display counterexamples. So for each leaf that we have in the decision tree, we show examples and we show counterexamples. I think the function of the leaves is more like to split things into kind of salient categories. So then you can further go into the category and look at like an example and a counterexample. So I do think that like clustering is kind of important for like to have an idea in your mind what the general patterns the things follow are. One interesting thing is like specifically for word sense disambiguation, or like choosing words with different semantic subdivisions. I don't think decision trees are the best way to do that. So it would be nice if we had like a translation model or a BERT-based model that we could then go in and interpret and explain the distinctions there. But yeah, that we tried doing that and it wasn't easy, so we haven't done that yet.
Yeah, I think so too. And I guess very much to a point, we would need better parsers to reliably do that.
Yeah, for sure.
Thank you.
And also for inviting us. Thanks for being accepted the invite and being here. Thank you so much.
Yeah, thanks a lot.
Approaching the end of this workshop. I don't know whether my other co-organizers is here in this room. Basically, I mean, I just want to thanks for everyone participating in this workshop, for all of the authors that we have, all of the great PC members, and also for NAACL committee for accepting this proposal and for this workshop. And we would like also to just continue for the next year. Actually, I mean, the first iteration of this workshop was in 2018, but also that time was the first of almost deep learning, and also that time we see that there is a lack of also interest on the working on the low resource, and we run it also 2019. Later, we see that also most of the works are running for the zero shot, few shot, and also just everywhere. And we run it again this year, as we see that also there are some other aspects of the work that also cannot be covered maybe in a different big conferences, and we wanted to also continue having these discussions in the multidisciplinary way, and also provide a room for people new to academia, and also just for that they are doing work on this area, but I mean with less resources and so. And yes, I mean also we want to consider for the next year also having a share task. If there's a good ideas also and you want to also contribute, also you are welcome to also just contact us for that. And yeah, again, I would like to thanks for sponsors for this year, Google and eBay. And we actually also just all of the sponsors, we just give it to the DEI group for this year. And that's all from for this year. And then thanks for coming here, and hope to see you again next year.
I don't think I have any possible impact on